scientific papers started to come out of people working on fruit flies. They found genes that control the development of the major architecture of the body and the right placement of the organs in the body. But what was really cool is that versions of these genes were not just in fruit flies. They were in worms, fish, frogs, mice, humans, all. And I remember thinking, holy cow, geneticists are unlocking sort of this evolutionary toolkit that could provide the basis for understanding the flourishing, the origin of diversity, And so that was a moment for me too, because here I was studying to be a paleontologist, and now I'm seeing this new molecular biology that's kind of revolutionizing the way we think. I'm thinking, oh man, I better learn some molecular biology. I'm going to go extinct just like the fish I want to find. So it's like, like change or die. So I had to. That's when I became more of a developmental molecular biologist. So my laboratory now actually reflects that shift in my life. I'm very much a fossil finder leading expeditions, but we're very much involved in genes and developmental genetics of living creatures, looking at the synthesis that we can have by merging these different lines of inquiry. And it's just another example, you have to be ready to change.
Hi, and welcome to the Origins Podcast. I'm your host, Lawrence Krauss. In this episode, I had the distinct pleasure and privilege to talk to an old friend and colleague, a distinguished scientist, a biologist, paleontologist, Neil Shubin from the University of Chicago, who has written a new book called The Ends of the Earth, Journeys to the Polar Regions in Search of Life, the Cosmos, and Our Future. Neil attained fame as a scientist for discovering a fossil which he called Tiktaalik, which I think is an Inuit word, but it describes basically the first evidence of a fish with legs. A fish that the first transitional fossil as fish began to evolve into animals that could live on land. The important missing link in the history of evolution of life on Earth. And that got him fame as a scientist. His book at the time, Your Inner Fish, which later got turned into a TV series, also was a best-selling book at the time. And this new book is equally interesting in so many ways. It describes the challenge of doing science in a polar region where he spent a lot of his time since as a graduate student. I'm a little familiar with that, having spent time in Antarctica and also in Greenland. And I know the amazing science that's been done there. And it has an impact not just on our understanding of our own human evolution, but the evolution of the Earth itself, going back and understanding our climate back 1 million years, understanding how quickly the climate can change, how ice itself can move so much faster than you can imagine. And also not just the Earth, but the cosmos, because in Antarctica, at least, you can look for meteorites, and not meteorites that not just tell us about the beginning of the solar system, but meteorites from Mars, which may one day reveal more information about life on Mars. The science is fascinating, but what's also particularly fascinating is this personal discussion of the challenge of doing science in such a dangerous environment. Now, the Origins podcast, of course, is in many ways about origins, and this is not just about the origins of the Earth, but in the book itself describes his own scientific origins, from the first time going out into harsh climates as an intern, as an undergraduate, and then a graduate student, when he hadn't even gone camping outside the house before, to leading expeditions to places where the science is hard enough to do, even in a nice environment. But these are environments that can kill you if you're not careful. It's a fascinating discussion. I really enjoyed it. He's an eloquent speaker, and the material is very interesting. And you can watch it on our Critical Mass Substack site, ad-free, if you subscribe to that site. And subscriptions to that site, the funds from that will go to support the Origins Project Foundation, the nonprofit foundation that produces this podcast. Or you can watch it on our YouTube channel, and hopefully you'll subscribe to that, or you can listen to it or watch it on any podcast listening site. And no matter how you watch it or listen to it, I think you'll be as fascinated as I was by this remarkable discussion of doing science literally at the ends of the Earth. So with no further ado, here's Neil Shubin. Well, Neil Shubin, I'm so happy to have a chance to talk to you again. It's been quite a while. Thank you so much for coming on the program. I've really enjoyed every time we've interacted before, and I know I'm going to enjoy this one. So thanks.
Thanks for having me on. Looking forward to it.
Yeah, I mean, ostensibly the reason we're on now is your new book, Ends of the Earth, Journeys to the Polar Regions in Search of Life, the Cosmos, and Our Future. And it's a great read, which I enjoyed going through, and we'll go through it in great detail. Some really interesting combination of personal stories and history about polar regions and their importance. But this is an origins podcast, and what I like to do is sort of begin by trying to find out how people got to where the starting point of our discussion, and I like to learn more people. I've known you for a while, but this is a good chance for me to learn more about you as well, and your backstory. Of course, you're famous for is it Tiktaalik? Tiktaalik?
You nailed it. You're very good. First try. Thank you.
Yeah,
Tiktaalik,
well, I've had a lot of Inuit friends at but anyway, for discovering, and we'll get there to the fish on legs, and that's a precursor in some sense to some of the things that are discussed in the book. But I want to go further back. You grew up near Philadelphia, I assume an affluent suburb outside Philadelphia, or?
Yeah, I grew up outside Philly in a classic sort of upper middle class suburb. I'm the last person you'd think would be a fossil hunter in the polar regions because, my family used to think that, camping was staying in a Marriott rather than a higher end hotel or
Mine
Motel
too,
6.
exactly. And I only know, I've been looking up trying to find biographies there, and they all begin sort of with your university, with Columbia and then Harvard. But I want to go back further. So,
Sure.
I don't know your background, your parents' background. Were they professionals? Were they academics? Were they what were they? What did they do?
My dad was a mystery writer. He wrote thrillers and mysteries of a noir genre back in the 50s and 60s and freelanced his whole life. So I grew up in a writing family, and my dad was freelancing, and he had all the ups and downs of a writer. And I would be his first editor, really. Even as a kid, like a 13, 14-year-old, he would give me his manuscripts for various thrillers and mysteries he wrote of a very noir style, very staccato, classic kind of Raymond Chandler-esque kind of thing. And I learned 2 lessons for that. I learned the power of the written word, number 1. Number 2, I learned it's never really good to criticize a writer in their first draft. So I'll be like, "Oh, Dad, this is perfect what you just wrote. It's absolutely perfect, but you can make it perfecter if you do X, Y, and Z." So I learned how to talk to a writer. But actually, I got a lot of my passion for the written word came from my interactions with my father and seeing him as a writer and so forth.
What
and
about
my mom,
the passion for?
Yeah.
What would your mom? Sorry to interrupt. Your mom?
Yeah, my mom was ran a day camp for a while, then a nursing home. She sort of was more of the management side of things, and and so she just juggled a business with being running the home, honestly, and then dealing with a writer as a husband, which can be really
which is always a challenge.
Yeah, exactly.
Had they gone to college, both of them, or were they college educated, or no?
No, my mom, yes. My mom, no, she did not go to college. My father was the first and only person in his family to go to college, so it was a big deal.
Did
neither of them were science. Say what?
What was that?
he studied journalism, and so he studied journalism, and so his whole thing was to follow the Philadelphia police force around when they did their midnight raids, and then he would get like official detectives kind of stories out of it, and then fodders. He had notes downstairs of all these different police cases that were later fodder in some way for his creative process and crafting his novels, and but he was not science literate. In fact, he was pretty science phobic. My mom was the same, and they were fairly religious, conservative Judaism. I was raised that way, so I was not raised in a science in a background where you think the offspring would become a scientist, honestly.
Well, it's not that unusual. I've talked about this too much in the program. Neither of my parents went to finish high school, but they did. But I'm wondering if it was a conservative Jewish household. There's 2 questions I had about you. One, I've learned about now why you might have started writing, because it clearly that's of interest. But the other question is why science? And in my case, it's because my mother wanted me to be a doctor, but I don't, coming from that kind of background. But it wasn't what got you into science, and also not just writing but reading. Were there a lot of books around the house for you, and other than mystery stories, or not? Or
Oh, there were tons. Yeah, tons. I mean, I think honestly, um, my favorite things to read were mysteries, honestly, and
yeah,
and
I still like
literature.
reading this.
I went through a huge Sherlock Holmes phase, and
Yeah,
that honestly, when I look back on it, was really sort of it just, you read about Conan Doyle later after
yeah.
Sherlock Holmes, you're very mystical, but with Holmes was, very rational, extraordinarily rational, figuring out the past by finding the clues and having that insightful way of seeing, just, detecting the important clues from the unimportant ones. And I just love those moments and those stories. And sometimes I reread them again because they bring back that youthful curiosity and excitement from reading them the first time. They're kind of my
Oh
comfort
yeah,
reads
I
sometimes.
love
Yeah.
going back to them.
Yeah.
In fact, I just listened to them all. My friend Stephen Fry narrated them all, and I listened to 62 hours of Sherlock Holmes. If you
Oh,
have
I love
time and a
that.
long
Yeah.
car trip, I highly recommend listening to Stephen's rendition.
Indeed.
But it's interesting that you say that I agree with you. Holmes was sort of the ultimate rational sort of, for most part, scientific type, and science is a kind of a detective story. But and sort of looking for clues and trying to piece together what happened, and was it through mystery stories, or was it through a good teacher? What got you in the direction of science ultimately then?
Museums and planetaria.
Ah,
I used to look forward to the days we'd go to the local natural history museum in Philadelphia, or the local planetarium. And I just, those environments really evoked a sense of wonder that hasn't much diminished, honestly, through my life. And, seeing the dioramas of the animals from around the world, the fossils and the dinosaurs, the planetarium displays. I just remember
yeah.
falling in love with natural history, with astronomy. In fact, astronomy was my first love. Um, and it largely through the encounters at the planetarium and then readings that I would do afterwards, just be so excited seeing this and seeing the awe and wonder. And remember, I was growing up at a time when humans were walking on the moon. I was 7 to 12 years old when the Apollo missions were
Yeah.
going to the moon. So science was a very forward looking enterprise. It was tied to national identity. It was bold. It was risk taking. This is the era of the great National Geographic documentaries, the fanfare for the common man,
Mm.
da, 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 and you'd see Jane
Right.
Goodall with the chimps and Carl
Yeah.
Sagan with Cosmos. Um, I just was just caught up in this tidal wave of science as an enterprise that's forward looking, optimistic, inspiring, full of wonder. Honestly, I mean, I'm still kind of choked up when I talk about it and I kind of touch that place in myself when I'm writing about it.
Yeah,
Yeah,
I
I was
agree.
growing up at a
Writing
special
often
time.
inspires. I mean, as someone who's written, I've often find it's nice to write because it rekindles one's own inner enthusiasm. Often when you write about it, it's really
Oh,
kind of
indeed.
nice.
Absolutely. I mean, those are the moments, those are the moments, you have a lot of moments when you're right. Some of them aren't so great, but
Yeah,
some of them, the really great ones are where you're touching a place in you that just opens up,
yeah,
a world of
that's
your own
right.
personal history, but also the way you see the world now and tying it to your past in important ways.
Now, okay. So you had said something that prompted me. I was going to always wonder why people don't do physics, but you're so your initial interest was astronomy.
Oh,
What
absolutely.
moved you? I assume I don't. Was your undergraduate degree in biology, or was it what was it?
Oh, it was biology and anthropology. I did a double major with a minor in geology. I actually did not do astronomy in
Mhm.
college. I took astronomy in college. I took actually two, yeah, I took a couple courses in astronomy in college, along with physics and all that, and which we had and math because it was all
You have
math at
to do
that point.
that stuff. Yeah, yeah,
Yeah,
yeah.
exactly. Um, but really what happened was I entered, so astronomy was a real love. But then I really
No.
loved animals. And I wanted to be a vet because that's what I knew, studying animals, maybe a zoo vet or something, treating the lions and the tigers and the bears, all that sort of stuff. And
Hmm.
so I went to college with sort of a natural history astronomy mindset. And
Hmm.
I went to college in New York City, And I took a course in my freshman year on human evolution. It was taught by a curator at the American Museum of Natural History. And it was once a week, kind of a 3-hour, once a week deep dive.
Mm-hmm.
And he would bring fossils from the collection or casts from the collection to the class. And I just remember it just captured my imagination that people could travel the world using sort of empirical conceptual tools of geology and other things and find physical objects, which can change the way we think about our past. And I remember thinking that. And then he offered me an opportunity to volunteer at the AMNH, American Museum of Natural History in New York. And I met the graduate students who were, they were going to China and Chile and Western United States, and they were coming back with all these adventures and ideas. And again, importantly, physical objects, which were telling us about mammal evolution or amphibian evolution and so forth. And I got swept up in that. Yeah. And so that's kind of part of my trajectory right now. And then, then I got invited on a field expedition in my third year in college. And I went on this expedition to eastern Wyoming in search of early mammals, Cretaceous mammals. And I was so bad at it that the curator professor at the end of it, took me aside, said, "Neil, I just got some advice for you. I know you want to do paleontology. Remember, there's two kinds of paleontologists there. There are those who work in the field and there are those who work on the collections. You're the latter." I'm like, okay, great. Like, because I was so out of my league, right? At working, in dirt and rock, it's not what I grew up in. So I was kind of out of my league on that, but I really loved it, and I stuck with it, and in graduate school, and fortunately,
you decided to go to. It's interesting. I think it's important to talk about sticking with it, by the way, because too often people, think that they get turned off. Even in physics, they're not the smart. They're not the best mathematician in their class, or not this. Other people seem to find it easier, and the point is that hard work gets you through, and really interest. It's more interest and enthusiasm almost than anything. You can overcome a lot of things and learn how to do things, and not always necessarily be initially the best. As I say, I have lots of friends who are Nobel Prize winning physicists who are not the best mathematicians in their class, or even or some of them even maybe having any background in experiment. And so it's often, people often say, well, I can't do that. I can't do science because it wasn't easy initially. And like anything, like music or anything else, you can eventually become proficient if you're interested.
Yeah, you got to stick with it. I mean, I think in a lot of this, it's just the persistence, and in fact, in a lot of the discoveries we make were actually that same sort of persistence, and just sticking with it, like you say. I mean, and just being patient with yourself a little bit, and I didn't know that at the time. I was actually quite impatient with myself, but I knew what I wanted to do, and I decided, to keep on it for a little bit, give it a try, and I'm glad I did.
And in fact, actually, the persistence comes from interest. Most scientists are not out to save the world. They're doing what they do because they love it. And persistence is important because, again, unlike the modern conception of scientific breakthroughs happen every day, you can't work for 10 or 20 years on something, most often failing, if there isn't something about it that fascinates you and keeps you going.
Oh yeah, I'm failing all the time. The question is, how do you deal with that failure? And how do you adjust and what you do? And in fact, I wouldn't be here today if it wasn't for all my failures, right? And so, that was a lot of it. I didn't know that as a young scientist or wannabe, but I knew but I was kind of fearless. I was never really, and I don't know, now I look back on it now, never terrified of failing. It never really bothered me too much to fail. Which is good because I'm very good at failing.
So. Well, Phil, one of the things we don't teach well enough in school, I created an entrepreneurship program once when I was chair of a physics department, is one of the things the entrepreneurs came back and told us when we asked them what we should be teaching was how to fail effectively. We give students things where they're designed to succeed, but in life and research or in outside, you're failing a lot, and how you use those failures is perhaps the most important lesson you can get.
Yeah, persistence, patience, passion, the 3 Ps, I think, are the ones that get you through it,
Yeah.
and the ability to learn on the fly, right? So
Yeah, and continue to learn. I mean,
continue
I
to
don't know
learn.
about
Yeah.
you, but often, first of all, I never took I've as a professor of astronomy for many years, I never took a course in astronomy in my life, but I learned a lot more physics and astronomy after my PhD than before, and I think that that's a really important thing is how much you learn after you get that credential.
Oh yeah, absolutely. No, no, no. I mean, it's like, that's why I'm in the field I am, because it's always learning. I mean, it just every day is learning,
Yeah.
and it's almost like the Red Queen. You have to learn just to stay in place. And if you want to get ahead, you really have to put it on a real burner.
Yeah.
No, I love that part. And it's also humbling. And I think that's a big part of it too. You have to remain humble, as you well know, in the face of the natural and physical world. I mean, there's just so much we don't know, and you have to be humble in the face of that, that just our own ignorance,
Yeah.
and and humble in the face of your own failing sometimes. And I work in the landscape where you actually have to, when you're working in some of the regions we work, there's a lot of levels of learning to do.
Hmm.
Not just the scientific piece, just like living in a polar region, for
Yeah,
instance,
we're going to
or
talk
working in the
about it.
field. Yeah, exactly. So there's a lot of learning at a level. There's a lot of
Yeah,
levels there.
yeah, I mean, I often think of that as a theoretical physicist. So I just sort of sit down and do my stuff. But in your, as we'll talk about, and when you're working at the poles, before you can get to actually do this stuff, there's so much other stuff that needs to be done just to survive often
Yeah,
and learn
exactly.
how to survive in the field. Um,
Exactly.
but, but we'll get there. But so you went after you got you went to Harvard and you
Mhm.
chose to, and you'd already chosen the organismal biology, which is a famous group at Harvard. Um, and why there? Why that specific part of of biology that got your
Right.
interest?
So that at the time at Harvard, this is like in the so this is the early 80s.
Hmm.
You had a really fabulous paleontology group, a fabulous evolution group, and there
Hmm.
was a very integrative way of thinking that the
Yeah.
paleontologists were also working on living animals. Many of them, there's a lot of bold ideas out there. There's, like Gould and Lewontin and Meyer and Wilson and all these luminaries were there. And as a graduate student, I was able to just go all between them, and it was really it was a very fun time, humbling to say the least. But no, it was really fabulous. And I remember I took a course in my first year, which was just changed the way I see the world. I was like, it was it was it was like the great transitions in vertebrate evolution, right? So
Hmm.
500 or so million years of
Yeah.
vertebrate evolution, and each week was a different great transition. And I had to present, and I thought I went to graduate school to work on mammal evolution, Cretaceous mammals, Jurassic mammals, to understand how they evolved to climb and things like that. And I had to present the week of the fish to tetrapod transition, the transition from life in water to life on land for
Mhm.
vertebrates. And I'm going through the papers and I'm going through it, and I just, wow, this is a first class scientific problem. Heck with the mammals, I'm going to do the fish. And honestly, I didn't look back because, there I saw, hey, man, this is a field that's ripe for new fossils, ripe for new thinking about maybe development and evolution. And so I was captured by that puzzle, and it captured my imagination. And that was my first year. And so then I started to think about, hey, how can we find
Wow.
fossils to tell us about that? Um, but then there was another revolution that happened at that time that also changed the way I think. And so this is like in the mid 1980s by this point, and scientific papers started to come out of people working on fruit flies. They found genes that control the development of the major architecture of the body and the right placement of the organs in the body. But what was really cool is that versions of these genes were not just in fruit flies, they were in worms, fish, frogs, mice, humans, ball. And I remember thinking, holy cow, geneticists are unlocking sort of this evolutionary toolkit that could provide the basis for understanding the flourishing, the origin of diversity. And so that was a moment for me too, because here I was studying to be a paleontologist, and now I'm seeing this new molecular biology that's kind of revolutionizing the way we think. I'm thinking, oh man, I better learn some molecular biology. I'm going to go extinct just like the fish I want to find, So it's like, like change or die, So I had to. That's when I became more of a developmental molecular biologist. So my laboratory now actually reflects that shift in my life. I'm very much a fossil finder leading expeditions, but we're very much involved in genes and developmental genetics of living creatures, looking at the synthesis that we can have by merging these different lines of inquiry. And it's just another example, you have to be ready to change. And I love the, and throughout my career, one thing I've always done is I've always had imposter syndrome. That is, when I go into a new field or a new wave of integration, and now we're doing it with robotics and physics and development, I'm always the new kid on the block, and I'm always behind the curve, and I don't really always feel that I'm the expert, And then when we do something, I feel like, well, I don't know, I don't really deserve it, because the pros have been doing it for a long time. But I'm just, So my career has really been a story of kind of learning and shifting and adding new things, and but always moving into an area where I'm outside my comfort zone, right? Fieldwork was outside my comfort zone. Working on fish was actually outside my comfort zone. Working in developmental biology and developmental genetics, totally outside my comfort zone. You know what I mean?
Yeah.
And then working in polar regions, completely outside my comfort zone. So learning is sometimes not only failing, but getting out of your comfort zone. And part of that might mean, exactly. And getting to a part where you're like, there's no guarantee you're going to be right or even make progress, but you're going to give it a go.
I wonder, that's, you probably, I resonate with what you said, because my background was in particle physics, and then I moved into cosmology, and it's a whole new field. And I wonder, for me, sometimes I wonder whether I like to go outside my comfort zone, because there are different kinds of scientists. And I have to say that, you certainly, your work on discovering our inner fish certainly was a long story directed towards a goal. But there's some scientists I know, who are great at focusing for 20 years on a topic and making progress in it. I personally like to move to new topics. I think some of it is just because it's just the way I am. I sort of like to hit and run in some sense. It's fun to learn new things and not, focus on one area. Does that relate to any sort of your own personal inclination as well?
Oh, definitely. I might stay interested in the same problem, but I might search new tools to find it, to dig into that problem, and that might change my mindset. Or I might find new problems. My lab right now is working on a whole new set of problems. We always are trying new things. And I'm fortunate to have a really great bunch in my lab. I'm really talented bunch of people in my lab who, take things in different directions and run with it. And I learn from them,
Well, look, I want to, before we get to I want to go through so many interesting topics in the book, but I do, because you're most well known for discovering something very important, which is how fish came onto land with Tiktaalik. And I want to just take a few minutes for you to walk us through that, because it's interesting to me that the first presentation you gave as a graduate student, in some sense, was about the same topic that ultimately your research would lead you to, which is mammals on land. And could you just give us a brief overview about how you got there and how that discovery took place? And one question I have that actually, I kept asking when I was reading the book, and it's not, you never, maybe because you've talked about it elsewhere and you presume one knows, but why is one driven to polar regions, mountains and polar regions, to look for fossils that are related to when fish came to land? It's implicit in a lot of what you say, but you never explain why are you driven there, other than, hey, it's fun to go there.
Because I did a bit about an inner fish, and I didn't want to repeat that. But
I figured that was the reason. But
But
yeah.
you asked the right question. So I guess what got me into it was actually a diagram that I saw in an intro textbook, honestly. So it's like, it had like a cartoon of a fossil fish that we knew about from rocks about 390 million years old, maybe a little bit older. And below it had an early limbed animal, one of the first creatures to walk on land, a cartoon again. And it was an intro sort of thingy. And I remember looking at the critter on top and the critter on the bottom and thinking, holy cow, that's a lot of changes that had to happen there.
Yeah.
And, maybe if we sort of targeted expeditions right, that we could fill a gap. That is, you had changes in the head, you had we go from a conical head to a flat head. You had changes in the appendages where you go from fins to limbs, lots of changes throughout the body. And I was thinking, well, if we found something more on the fishy side of this, that's sort of a proto-tetrapod, but kind of a fish, that would give us a great understanding of not only this particular transition in the history of life, but maybe we can understand general principles about how these transitions might more generally happen. Are there ideas that would emerge? And so there was a lot at stake for finding, sort of this object that would tell us about the transition. And so I was actually studying to be a paleontologist before this molecular biology stuff hit the scene. And so I was learning that toolkit, which is, you go to places in the world that have rocks the right age to answer the question, rocks the right type to answer that question, maybe rocks that are exposed and accessible. So you have a series of filters: age, type, accessibility. And, you take this globe and you apply those filters, looking at the geological literature, geological maps, satellite photos, aerial photos. We have all this information about different parts of the world. And it became clear from understanding of what other people have found was there were a lot of discoveries that had been made up to that point. This is like mid 80s, early 90s. A lot of discoveries by that point, many of them really, really cool and very important. But they pointed to us to the fact that maybe we want to look at rocks around a particular time period, 375 million years. We wanted to look at rocks that were formed in ancient rivers and streams draining into the ocean. So something that would take us from like a tidal flat, an estuarine environment, all the way upstream into rivers and streams. And then to look for the geological signature of those environments. So that's huge clues right there. I knew I wanted rocks of a particular age. I wanted rocks that were formed in particular environments. And then I needed those rocks exposed at the surface. Three of those major criteria. And so, with those lenses, me and Ted Deschler, who was my partner in all this for years. So it was my first graduate student, and we've been colleagues ever since, partners and co-PIs ever since. It became clear that, one of the great places to look, although there are a couple others that haven't been looked at, but one of the great places to look that was completely unexplored was the Canadian Arctic Islands, essentially extending from Ellesmere Island all the way in the east to about 1,500 kilometers, all the way to Melville and Banks Island, all the way to the west. The Canadian Geological Survey published some amazing papers and maps. I mean, Canada spent an enormous investment in mapping the rocks up in the Canadian Arctic, largely for national reasons. Nationalism was what drives a lot of this, maybe the possibilities of extractive industries or other things. But in this case, actually, it was Cold War, too, because, that would be the pathway for nuclear missiles shot from the United States to Russia, and they needed some gravity,
and the
other way as well. Right. So they had to understand how the gravity would be acting on these things. So they wanted to know the rocks there. So we had at our disposal of stuff, and it was really clear, bingo, this is the place to go. And so it became clear that was the case. I was like, oh, Ted, what do you think about working up in the Arctic? This is going to be a whole new gig. He's like, I don't know. What do you think? We'll see. Try it. Give it a go. And so, that was in the mid late 90s. And then we had a new problem, though. So that's what led us to the Arctic, right? It was because of the rocks in the Arctic that they're perfect for this search. And it turns out the rocks in Antarctica were pretty good, too.
Let me stop you for a second, because it's not there, but I presume the point is, when you talk about the right time, I assume from studies of organismal biology and evolution, the era where fish first moved onto land was was temporally defined, estimated to be a certain a few 100 million years ago,
Yep.
and that determined the age of rocks you were looking for, and so,
Yes.
go on.
Yeah, that's right. I mean, you got it. And so, because basically you have a lot of fossil amphibians with fingers and toes,
Yeah,
like in the late Devonian
yeah,
period, around
yeah,
365 million years. And you have a lot
yeah.
of fish that are kind of starting to look a little bit like them, but that have fins and, conical heads a lot earlier. And
Yeah.
so you can constrain it that way. And honestly, we take
Yeah.
it a little more detailed. We use evolutionary phylogenetic trees, and we calibrate them over time. So we have these time-calibrated phylogenetic trees where we take the stratigraphic record, the geological record on one side, the evolutionary trees on the other, and we can see where the gaps emerge. And again, you're dealing with estimates on either side. They can be wrong. So you're always sort of kind of tying together estimates on either side to make another estimate of where to look, right? And then that's what led us to the polar regions, not the ice. It was the rocks that did it. And
And again, just so I can step back for people, so the idea is that you might say, why do you look in a certain place for a certain time? And the point is that the dynamics in the earth, and certain rocky regions from certain times have been pushed up and are exposed because of glacial dynamics and because of global tectonics. And therefore, in certain regions, the exposed rocks are characteristic of a certain time. And the times you were looking for around 300 million years ago were rocks that are exposed in the Arctic. Is that a fair?
About 300? We're looking again 375 million years ago.
Yeah.
But yes, and so so remember, the continents are always moving, rocks are always eroding. And so what is now in Ellesmere Island of Devonian age rocks was actually formed when that landmass was closer to the equator, 380 million years ago. So moved up. Which creates this incredible juxtaposition between present and past. And that I felt that really acutely, in Antarctica, but very much so in the Arctic. Here you're standing in the Canadian Arctic, at a latitude of about 78, sometimes 80 north. There's glaciers at the head of the valley you're working on. There are muskox in the distance, maybe a polar bear trundling along. Yeah. And you're working on a tropical world inside those rocks, right? You have this juxtaposition between, present and past. It just shows you how much our planet is capable of change, right? And so that's exactly what led us there. And then, so then we had a new puzzle, right? Now, okay, we know this region in the Arctic is kind of ideal for finding these things, but the Canadian Arctic is a very, very, very big place. And these fossils are relatively small. How do we, where do you go? What do you begin? How do you do this? And I remember viscerally feeling this when we led our first expedition there in 1998, landed, it was 1999, landed in the Western Arctic of Canada, and the plane took off, and we had all our food, we had all our tents, we had a crew of 6 people. The plane takes off to go back to the base in Resolute Bay, which is a couple hundred miles away. And we're all looking at each other thinking, what the hell are we going to do now? It's like, we're out of luck. Now what? Okay, we had a great idea in Chicago and Philadelphia. Now what? What was great on paper is now we got to walk this thing out. And then you got to do the hard work. And then, that's when you got to really think about the geological record, what rocks are likely to hold the fossils. Then you got to look at them. You got to walk to them. You got to, or fly over them, or, you got to make it work. And that's the the boots on the ground piece is really challenging, but that's, but it takes time, and we just stuck with it.
Well, yeah, I mean, and there are lots of stories we'll go over about taking time, but I would, and I want to get now to the book, but the last thing I want to say, so just so people know, put in context, from the time you started to look, you knew where you sort of wanted to go and where the clues were, and Ellesmere Island and the Canadian Arctic. How long was it before, from that initial moment to the discovery?
6 years.
6 years. Yeah.
Yeah. So 98 is when we had the idea, and it became very clear this is what we want to do. And mid-July 2004 is when we cracked that first rock, and there it was. Yeah. And that was like
Wonderful.
both a wow and oh my God, thank goodness moment.
But that's yeah. And there's a lot of years in between where you're cracking a lot of rocks and you're not
We're
finding
not
what you
finding it.
want.
You got it.
And I think that's important. And there are lots of examples on that. And so great. I wanted to give that personal history of how you got there and why you go to the polar regions, which I think is an important precursor that maybe that is useful to add to the book. I think is sort of to before you go to the book, why did you end up on these weird, other than hey, it's fun and this is neat, why go there? The book, what I like about it is just like the discussion we had. It's a mixture of discussing science, personal experiences, politics, and also ultimately the future, which we'll talk about. And I want to go through that in those things in some detail because there's lots of fun stories, but there are lots of important lessons, I think, to go through. And I actually want to start at the end. I was particularly taken by a story in the epilogue, which I think, which you, as you say, in retrospect, gives you sort of a picture of of really what you've talked about, and that's the story of these plover eggs. And
yeah, it was crazy.
And yeah, I love that story, and I wonder if you could talk about it here because I think it's a good, even though it's the epilogue of the book, I think it's a good way for us to segue into the issues that you're going to talk about, that we'll talk about together.
Yeah, so I was invited on a polar expedition in 1988, joining 3 seasoned paleontologists. I was a lone student on that thing. And, I was not particularly really well prepared for it. I was not cut out. I mean, you would not have seen me as somebody. It was one of my first camping trips, right?
Yeah.
And here I'm going to like East Greenland, living in a tent for 4 to 6 weeks, and that kind of thing. And there's a lot of vulnerability associated with living in a tent. There are polar bears around and you're in the food chain, and I felt profoundly in the food chain, but also the weather and things like that. And I was pretty scared the whole time, which is good. Good to have a little fear.
Yeah.
And I remember I said such things. Ever the nerd, I brought field guides to birds and mammals of North America. We had a strict weight limit of what we could bring, and I had about, 40 pounds of books, It was like, and half of them were like field guides to like bugs and birds and mammals. And so, in the early days we were walking, where we set camp, and this is a problem a lot of times with working in polar regions is you have to choose the right camp spot near the rocks, and if you don't choose the right camp spot, and it's non-trivial to do that, you can be out of luck, because if you can't, there's no roads, there's no, you can't just call an Uber to get to these things. You have to take sometimes a pretty long hike, and that's what happened in this first camp. And I remember we had this long hike, and I ran and it would be like a 2 or 3 hour hike just to get to Promising Rocks. So look for the fossils we were after. We were actually, in this case, looking for early dinosaurs. I was on somebody else's expedition, and early mammals too. And I remember I saw this bird, and I'm like, oh, a bird. Oh, I got to identify this thing. And it was like clearly not doing well. It was dragging a wing, and it was flapping the other one, and it was chirping really loudly. And I'm like, damn, that thing's hurt. And so I walked up to it, and I like took off like 6 feet away. I'm like, oh, let me just check it out. So I just followed this like wounded bird for a little while. I don't remember how long, until I realized I'm never going to get this bird. It's going to do its thing. I'm sorry. It is what it is. And I went to that later that night, or another later night, I went back and worked with one of the seasoned veterans and went through one of the field guides. And it turns out it's a black-necked plover. And they have a characteristic defense that they can lure predators away, where they fake an injury. And what they do is they have a nest, supposedly, I didn't see it yet, and they could fake an injury by dragging the wing and chirping real loudly, and that way they can keep the fox or the raptor away from the nest, and they keep on luring it away. So they treat these predators just like suckers. Well, guess what? I was that sucker too. And I was like, oh, wow. I just felt like an avian ruse that's probably millennia old, and it's fooled every animal. Now it fooled me. And I remember thinking, okay, I'm going to find this nest. But I didn't want to disturb the birds, right? Because it does cost a lot of energy for it to do this display. And I felt guilty. I didn't want. Anyway, had to hike through that spot a number of times to get to we were working in Triassic age rocks at the time, about 200 million years old, to get to those rocks. And eventually I saw the nest. And I remember just being profoundly affected by seeing this nest. It looked like the rocks. It was just basically 3 eggs, each the size of, I don't know, like a Brazil nut or something, colored. And there's this, it's not even a nest. It was just something like a pile of tundra dirt and rocks. And it was like, and I'm thinking, these little creatures are so exposed at the surface that they're developing, and there's foxes and polar bears and muskox and raptors and gyre falcons and you name it. And the elements, you have like 70-mile-an-hour winds and polar storms, and they're sitting naked on the surface. Their only protection, their camouflage, and an adult who can lure predators and sometimes humans away, with their as suckers in their dance. Mm-hmm. And I remember feeling profoundly affected by that. I was like, this is my first expedition there, as a student. And I came back and I actually wrote in my journal that day about that. And I wrote this thing, I wrote a poem called, I Am the Plover. It was the dumbest poem ever. I thought it was like brilliant literature, but it was like, I read it years later. I'm like, oh my God, I can't believe it. Anyway, I wrote this embarrassing poem, but it captured something in me that again came out when I was writing the book and I was writing the epilogue, that whether in the helicopter over parts of Antarctica or in the field or at the tops of mountains or on traverse or whatever, that image of the plover really stuck to me because it gives a sense of the endurance, the resilience, the subtle harmony and vulnerability of the life and, in fact, these regions themselves, and that vulnerability is something I felt profoundly as a scientist working in these regions. Like feeling akin to feeling the plover image inside of me, but also it's a metaphor for these regions, that how profoundly fragile they are, and how they've changed over millennia, and importantly, how we as a species are so tethered to these remote and fragile and vulnerable places that much of what we take for granted about our world today and what will guide our future is happening is changes that are happening in the northern and southern most extreme regions of our planet. And it's funny, as I was beginning to think of the epilogue for the book, that the plover image just came out of me, and then I dug out my old field notes and I ran into my embarrassing old poem, and I'm like, okay, well, maybe we can do a little bit better, almost 40 years later.
I'm glad you didn't mention the poem because they might have taken away, because obviously I'm returning to it because it affected me. That image
Thank you.
Stayed with me, and it's a wonderful image. And I'm going to read what you wrote there. You've expressed it eloquently anyway, but I think it's a nice introduction to where we're going to go. Journeys to the ends of the earth help us see ourselves and our home in new ways. Like the plover, humans live in a fragile balance with the planet, one that, for those of us who do not live at the poles, is masked by our built environment. A human body is a speck in a continent-sized sheet of ice. Our lifetimes are tiny moments in the multi-billion-year history of the meteorites inside glaciers and rocks and valley walls. And we live in a relationship with a planet that's capable of dramatic environmental change. And I guess if I had to sort of summarize in some sense what the book is all about, I think that really captures all of the different things. And I thought it was a nice way to sort of take us to there. And then I want to go to 2 quotes and I ask you to comment them right at the beginning of the book. He says, science in the polar regions means confronting emotional, physical, and logistic challenges in order to ask fundamental questions about the past, present, and future of life on our planet. And then another facet, which we'll come back to near the end of our discussion. For European cultures, polar science began as a nationalistic enterprise, driven by attempts to achieve or exploit the points farthest north or south. The race for the poles, or the discovery of the Northwest Passage connecting the Atlantic and Pacific Oceans, pitted nations against one another in often tragic attempts to be the first to arrive at certain destinations in the globe. Scientific discoveries emerged as teams mapped these regions and studied the natural history of peoples, planets, and the climate of the new terrain. So I think the combination of the challenge of working in that region as a scientist and an individual learning, and the fact that a lot of the science was done ended up being sort of peripheral, in the sense that the reason these regions were explored were first nationalistic, and later on, now it still may be nationalistic when we talk about resources as the polar
Absolutely.
region change. And so I just thought I'd ask you to comment on that a little bit.
Yeah, I mean, I think in some ways, our understanding of polar regions, it mimics kind of what we know about the moon, right? I mean, the Apollo missions, I mean, science wasn't the primary, right? Science was a big piece of it. There's just no doubt. But it was a nationalistic enterprise.
Yeah.
But we learned a lot about the solar system from the geochemistry of those moon rocks that came back. We learned about the origin of the moon. We gained some insights into the origin of the solar system and so forth. And that was a byproduct, really, and it wasn't the direct goal. And I think a lot of these expeditions that were run by European explorers, many of whom ultimately ended up deploying Inuit technologies to survive up there. There were so many theories about these extreme areas of the world, these extreme environments, some of them crazy today. But they were able to, test those theories. They developed not only the science of studying the polar regions, but the science of exploration, how you do it. How do you survive up there? That the polar regions tell us about this, like the subtitle of the book, they do tell us about life and the extreme adaptations of life. They tell us about, the cosmos, from, giving us a window into the solar system and beyond, and even some of the telescopes earlier. And also, our world and how we're tethered to these regions. But to get to that, really, and I guess what I wanted to capture with parts of the book was, and particularly for somebody who wasn't raised as somebody who ever really camped or anything like that, I had to learn about myself, and not all of it's pretty, about overcoming limitations. Helicopters break down, storms like this past summer wipe out camp, and you worry about people who are injured in camp, and all our food was across the tundra, and this was just in past July. And we had to be evacuated. And, there's humility with that, but there's also, just being able to handle these situations really takes a lot of patience with yourself, takes patience with other people, takes patience with the landscape, and to do that, you really do have to be in learning mode all the time. That's kind of why we do science and exploration, right? It's not always pretty though.
And something, again, for full disclosure, I've become fascinated by the polar regions, and not obviously my own work. Well, my own work almost brought me to the South Pole once, but I've been in Antarctica and led to West Antarctica, and then up in Greenland, and it is fascinating to me, and the allure of it. I understand why people get driven back, go back there over and over again, and some people live there. You might think it's so desolate. There's something magical about it at the same time.
There really is.
But there's also, as you point out, the challenges of survival, and then even in the very beginning, which you talk about later on, of course. I remember the first time I was in the north of Norway, in Tromsø, Norway, in the summer, and the light is a challenge, right? Because totally. For me, I don't know if you've ever had this experience, but during the week I was there, the weather was such that it was cloudy during the day and clear at night.
The worst.
Which meant it was much brighter at night than it was during the day, and for me that was such a strange experience. The night was the bright time, the day was the dark time.
Oh yeah. There's a lot to adjust to when you first get there, as you just described. It's kind of very well, actually. I mean, we're living in a tent in the middle of 200-300 miles from base, and it's daylight 24 hours a day. And what happens is, you have to adjust all your body cycles to this. It's challenging because you realize we are circadian animals.
Yeah.
Many of the cycles inside our body, all of them, depend on the night, light, dark in many ways. And you can enforce that on yourself a little bit. You can wear eye shades and, and typically what happens is you're working so hard during the day, at least for what we do, is in a minute you go in the sleeping bag. It's a joke in camp, by the way, where like I go into the tent at, it's 9:00. We keep on a regular schedule, not so.
Yeah.
If you don't stay on a regular schedule, you can go a little crazy. So
you talk about that later. Your
right.
rhythms go, you change, and people do go crazy. Literally.
You shift, and so to not go loco, you sort of enforce the schedule. So I black out with wearing eye shades at around 9. But I'm famous for going into the tent. They hear the zippers all close, and I'm snoring about 15 seconds later. You fall asleep so fast. I do it
because it was hard.
And I'm so tired, and there's no internet, there's no disturbance. You just whatever disturbances are, that's what you brought inside you, right? And so, but the problem is, you have to hydrate like crazy and drink a lot of water. So come 1 or 2 in the morning, you're thinking of, oh man, I have to get out of this sleeping bag because biology is, biology. And then, getting out of the sleeping bag, getting out of the tent, you take off the mask and you're,
boom,
daylight. It's impossible to go back to sleep. So that's the trouble, and that's that kind of. So I learned to keep my eyes closed when I go out of the tent. There's bio breaks.
Yeah, you talk
and
about
then your wrist, then you fall. So it's never pretty.
Yeah. Yeah, that's I know that experience in a number of ways, but it's but I think that's an important feature, but also at the same time, what you realize when you're there, and again, the context of the book is these regions, which for most people are just, they might read about or hear about and are remote, are nevertheless connected so intimately with our history and change. You point out that polar regions encompass 8% of the total surface of the Earth, 70% of the planet's fresh water is on it, and permafrost in the polar regions, which we'll get to at the end, holds 1,600 billion tons of carbon, which is double the amount in the Earth's atmosphere. These regions will impact us, and what what you don't realize in a human lifetime, we always think the world has always been the way it is and will always be the way it is, and it's a natural thing to assume, is that there's been tremendous change. And the first example of change, in some sense, is the realization of how, as you point out, of the fossils you're looking at in the polar regions were once in the tropics, and that kind of change jumps out at you there in a way that sort of we often don't recognize. And something that I actually hadn't really appreciated till I read the book enough, I guess it was implicit in some sense, is this notion of polar regions is itself recent. Is the fact that we have ice in the north and south sounds like, oh, well, there always should have been, because after all, that's the way they are. But until 34 million years ago, it wasn't that way.
Exactly. No, that you described it incredibly well. I mean, we're so biased by our own experience. There's ice at the polar regions. Well, that's kind of rare that's not the common mode in the history of our planet. There've been, most of the time there's no ice at the poles. Sometimes there's been ice at one of the poles and not the other. Another time, short times, there's been times when the whole Earth froze over. And then there's been long times when, again, there's no ice again. And then now we have ice at both poles. And so, these poles are very dynamic. So like this book is about the science of Earth's polar regions and how it changes the way you see the world. At least it did for me. And when what you describe is like, standing in atop a mountain in Antarctica and, finding these tropical fossils, yet being surrounded by the ice plateau in every direction, it shows you the juxtaposition of present and past. It shows you how much our planet is capable of change over these long geological timescales. But the more you look into the glaciers and the oceans and the climate, the more you realize that changes can happen extremely fast, that they've happened extremely fast in the past before humans. And now that you add humans to this again, we really are at a bit of a knife edge with regard to what can happen with the ice at the poles. So the ice comes and goes, that it actually can change really rapidly. And it's that sort of changes that can really impact all of us who live closer to the equator.
Yeah, in fact, that'll be a lesson we'll get to. But some of the change has been remarkable as we talk about, what humans are doing to the planet, and people say, well, geological time doesn't matter. But then we realize there've been dramatic changes that have happened quickly, and we'll get there. One of the first realizations that things change was the fact that ice isn't static because it moves, and
yeah, it's crazy.
And that was a great discovery that the ice, from one part of Antarctica, moved right across the continent. And I guess it's kind of interesting that it wasn't until the 90s, I guess, that we actually had a ways of really measuring it, but from space, from using space. And
Yes.
Maybe talk about that for a second.
Yeah, it's basically, the remote sensing, from space has really changed the way we see ice. I talked about Eric Reno, who's just an amazing scientist, studies the glaciers. And he's been, working at University of California, Irvine, but also Jet Propulsion Laboratories, really thinking about, the kinds of devices to measure the changes in ice. Because, from space, what you can do is you can look at the entire ice cap. You can monitor it every day, every hour. You can get very refined measurements from space. They shoot these lasers down, they ping them down and ping them back, and they can get a sense from that at a very fine, down to a micrometer, almost a micron, how much the ice is changing in terms of its height. They can look at movement of relative parts of the ice. They can, using two satellites tethered to one another, look at the changes in the height of the ice and the changes of the thickness of the ice, because they can look at the gravity changes.
It's a great mission. I have to.
It's incredible.
Say, to me, as a physicist, when I was writing a book on climate change, I learned a lot about the Grace mission, and it's amazing. I think I can't help but to mention it briefly, because when you talk about how different parts of science come together, who would have thought that precision ability to measure gravity would be really important for studying the poles? And it's a really neat idea. And again, as a theoretical physicist, I would have said, nah, it'll never work. And then these experimentalists can always do it, where you fly these satellites together in tandem, and they keep the same distance, which, by the way, in other areas of physics is now going to become very important as we look for gravitational waves. And then the point is, if you can measure it with light, you can measure the distance between those satellites incredibly accurately. And as they go over the Earth, when one gets to a region where there's more gravity because of a mountain or something else, it gets tugged a little bit, and that changes the distance a little bit. And amazingly, that allows you to measure incredibly precisely, as you point out, not just where things are at a micrometer, but later on also how much ice is, say, on Greenland. Because you can, see, because a lot of ice means a lot of gravity, and it's amazing how you can use these techniques to from one field to measure another. I love that. That's a facet of science that
it's amazing. Love. So one speeds up, one slows down, and they're coordinating, and the light can give precise measurements, and they can measure the gravity changes, i.e., the thickness of the ice, and they can do it every day, all day, with clouds, without clouds. Greenland, Antarctica, you can get. Just the science. When you write a book, you touch pieces of yourself in terms of the emotional and the connection and awe and the wonder. But every now and then often you touch science that's the same thing. It's like, it just blows your mind,
Yeah.
And they call one Tom and Jerry. They're Tom because presumably Tom's chasing Jerry.
Yeah, Tom and Jerry. It's and I think you've had that same thrill writing books as I do. I
absolutely.
like to write subjects because it's always amazing to learn about other science. You get wrapped up in your own, and it's just shocking and wonderful to see how much is done in other fields. And that's what I love about writing. But it's also, your point you just made is an important one that I wasn't going to emphasize, but I think it is probably important to emphasize, that it is remarkable how our understanding of the Earth has changed completely because of our access to space. And how tragic in some sense it may be that the current administration is more or less suggesting we end study of the Earth from space, or removing funding for it. It's really unbelievably tragic if that happens.
Yeah, it's a self-inflicted wound. It would be of tremendous proportions, because what these what these satellites have done is they've changed the way we see the Earth. Okay. So
Yeah.
like for a long period of time, like when I was taking my intro geology classes, we learned about Antarctica, and we learned about, Antarctic ice is the stability. It's the,
Yeah.
yes, it's come and gone, but it's, the last thing to change on this Earth. And then what the satellites have done, and as well as ground truthing with people working seismically on the ice and doing other things, shooting robots down and so forth, it showed just how fragile that ice is, how much it can change and how fast it can change,
Yeah.
that it's anything but stable, and that, as you mentioned earlier, that ice is always moving. There's these ice rivers, these ice streams that move maybe 1 or 2 kilometers a year. So the ice is moving from the center of the continent towards the coast, and sometimes it's moving very fast. And in fact, that rate is actually increasing. And so ice is incredibly dynamic. And one of my colleagues actually made the comment that, ice does not move at a glacial pace. And I actually put that in the book. It was just such a great line.
Yeah. It is a great line. Well, okay. And the movement of ice, which will become important later on, we talk about a variety of things. But also, I want to talk about now one of the first kind of fascinating bits of discovery, which has been aided again by space, although not initially done so much, is the realization that not only, that ice, I think you pointed out, and many people do, that the Inuit and many other people have many different words for ice, because ice is not just ice. Ice changes depending upon where it is and its characteristics. And that is fascinating and important for not understanding how, say, Antarctica works, but understanding how we can then use ice to study our own history and the evolution of the planet and life on the planet. And one of the features of that ice is how it changes with depth. The simple physical property of ice, that its temperature freezing depends on its density and pressure. And one of the great discoveries that you talk about early on, which is really kind of fascinating, is that there are lakes under the ice in Antarctica. And it's something where, again, we're learning using space probes to help us with.
Okay.
And it's telling us a lot that'll be probably relevant for study of life, not just here, but elsewhere in the universe. So why don't you talk a little bit about that, about the lakes under the ice and how that was first sort of realized?
I mean, so one of the things, this book was born largely, not only living in it, 40 years of almost 4 decades of working in polar regions, but also being in the scientific mix, in the scientific bases in Canada, Resolute Bay, or in Antarctica, McMurdo Station, and being in these places where scientists are coming and going from around the ice and the continents, and glaciologists and zoologists and ecologists and cosmologists. And it feels like Mos Eisley Spaceport, the cantina scene, with all these different kinds of people together. And it was there that I learned about these lakes under the ice, and it blew my mind because and the history of it's really beautiful because, it was proposed by some Russians that there should, based on that sort of the pressure density relationship of the freezing point of ice, that you should have fresh water under the ice somewhere. And then one Russian working at this Vostok station, which is in the middle of the ice cap, a crazy place, hard to get to.
It's an awful place.
Yeah, it's famously terrible. They found that the ice in certain parts around Vostok is kind of flat. It's not ruffled. So if ice moves over continent, which is always moving, it'll have contours and shapes in certain way, driven by the changes because of the friction underneath the ice. But there it was kind of flat, and had other properties too, which suggested maybe there are lakes under the ice there. They did a series of drilling projects and then found almost 2.5 miles under the ice in Antarctica. They found a freshwater lake. This is just the first one that was estimated to be about the size of Lake Superior, the Great Lakes, had islands in it that had fresh water. Yeah. And, that's kind of, when you think about that alone, that just tells you just how much we have to learn about our world. But then NASA figured out ways to assess that from space, and that was calculated. The calculations vary somewhere between 400 and 600. I think the maximum is maybe there's about 600 of these lakes underneath the ice. And the American U.S. Antarctic program has drilled into 2 of them to sample them. But, you think about just the surprises that exist in this world. And, and what it took to get there. Doing that drilling project was non-trivial. They had to, you only have a month, a year where you can get supplies there. Stuff breaks. You got to do it in a sterile way. And oh man, it was just, it was something. But you have these lakes under the ice. And what we don't know is how interconnected they are, right? You might have a whole world of you can have lakes that are isolated. You can have lakes that are connected with each other, maybe through under ice, sub-ice rivers, subglacial rivers. You might have them connecting some cases with the ocean nearby.
Exactly. So they may be flowing out to the ocean like more lakes.
Right, exactly. So, just understanding the map of the world. We know more about, parts of the moon than we do our own planet. We know that that's a metaphor, obviously, for the deep sea, but also underneath the ice is the same sort of thing. And where the rubber really hits the road scientifically, I think, is, when those waters are pulled up and people apply metagenomic technology, they can either, you can look under the microscope, but better yet, you can sample all the DNA inside there and get a sense of if there's anything living. And they find whole communities of microbes underneath the ice, and, that have been probably separated from the surface, maybe for millennia, if not millions of years, or communicating with one another through unknown rivers of ice. It's crazy.
And that first of all, you have to worry about it because, well, first of all, you got to ask, are these really isolated? I mean, obviously, if they're flowing in the ocean, they're not isolated. But if there are ones that are 2.5 miles deep that are isolated, they have been isolated for not just thousands of years, but hundreds of thousands of years or longer.
Maybe millions. Exactly.
Because then you're looking at early life if there are microbes down there. And the first question, I think 50 years ago, when you and I were younger, everyone would have said, nah, there's no life down there. And now we've learned, of course, life is everywhere. It's extremophiles are everywhere. And then you want to say, wow, I can sample directly life that may have been separated from life for hundreds of thousands of years at least. But then you got the problem if you drill down, you want to make sure you don't
mess it. Yeah, exactly.
You don't want to contaminate it because then you screw up the whole experiment. And
it's like exactly. That's scary. And I was down there in 2000. I was down in Antarctica in 2000. Last time I was there was in 2019, pre-COVID. And the team that was drilling into one of those lakes was there.
Yeah.
They had a whole technology where they had, hydrogen peroxide, they had UV lights, they had robots. They really designed technology that was highly sterile to get down to what, at the time they were drilling into one called subglacial Lake Mercer, which is one that might be connected to the ocean, but that's where they pulled out all kinds of microbes. Yeah. So.
And the interesting, there's tons of microbes and whole communities of microbes. And as you point out in the book, and before we go further than microbes, that I think you mentioned there, if not elsewhere, that obviously an area that I've thought a lot about is life elsewhere in the universe, and it's kind of fascinating to me this emerging field of astrobiology, which is almost a science. I would say not quite yet one, because it's mostly speculation because we don't know, anything about life elsewhere in the universe. And what we realize is how little we understand about life on Earth. And it often seems to me that the most important astrobiology that can be done is the biology that's being done on Earth, because then we learn about how life evolves in a way that might give us data, which could then allow us to better probe elsewhere in the universe, including ultimately when we, give us better reasons for knowing whether we should go to Enceladus and Europa, moons, where we now realize are probably the prime places to look for life elsewhere in our solar system, which could, in principle, be not related to life here.
Exactly.
We'll get to why life on Mars was interesting, but it might not be so interesting in terms of being independent. And we'll get there maybe, but these are moons which do have oceans, and the life there, if there is life, would have been separated from life elsewhere. And we have a great testing point here in Antarctica. I'll throw it to you.
Yeah. So in Antarctica, you think about these communities that exist under the ice, and honestly, we don't know much about them, right? We've only sampled a couple of these subglacial lakes. There's a whole world of life. There are whole ecosystems we have not even discovered yet underneath the ice of Antarctica, right? We talk about Nazi bases and aliens and, and H.P. Lovecraft monsters under the ice. But the real world is kind of amazing too, that we have all these ecosystems, and they're chemotrophs, right? They're separated from the sun, so they're getting their energy from breaking down, molecules and so
Yeah,
forth.
totally different
And
metabolisms,
it's
which
totally
are
different
new, I assume,
metabolisms.
in many places. Yeah,
And the waste product of one becomes the nutrient for another, and so they form this interleak chain,
unity.
this trophic chain, which is incredible. And you think about the insights that we get from these extremophiles and these isolated forms to think about life on the other planet. I'm with you there, because you think about what the Europa Clipper was just launched in October
Yeah,
24 to go to
yeah,
Europa to begin to map that surface, and that's the first step. And when I was talking to folks in preparation for the book about maybe a mission to Saturn's moon, what Enceladus, and how do
yeah.
you say it?
And,
Enceladus or whatever.
well, I say
Um,
enchiladas, but I don't. You never know. I never
I
know
say
how it's going.
Enceladus, you say
Yeah,
Enceladus. It's all the taste
yeah,
the same.
right.
Um,
Yeah,
but the again, that's a mission there would be, because they have the warmer water that plumes through the
yeah,
ice, and you can
yeah.
see
You can
those
already see
giant plumes.
the geysers.
Yeah.
Yeah,
No, I think to give us a model of how to think about what metabolisms to look for, what to think about geochemically. So when you have a model of something like the life underneath the ice of Antarctica, you kind of get a sense of what kind of metabolisms arise that allow creatures to break up chemical bonds and to use the waste products of one species for the nutrient of another, and the kinds of links that can form. Knowing those kinds of ecosystems could give you a sense of what chemical signals might exist in the waters that would tell you about life
yeah,
itself. So when you're looking for signs of life elsewhere, I think these extreme environments that model what exists elsewhere in the solar system might give us a clue to what to look for in terms of the kinds of devices that'll be necessary to take to
exactly.
space to monitor there. What sort of signals might be indicators of life versus indicators of an inorganic world. Um, that kind of a non-living
And
world.
and
You
it's
know
a
that
and also how to take the technologies that we use in Antarctica, namely the ones that ensure we don't contaminate the water
exactly.
there, make sure we refine them for ones that can be used remotely if we ever do drill down in Enceladus
Yeah,
or
yeah, it's exciting. It's really
and
exciting.
well, I wanna ask you a question. I mean, by the way, I always tell people to take every claim of habitable planets, life elsewhere in the universe with an incredible grain of salt, because specifically because we don't even understand, life here on Earth enough to know. But there are two things about these lakes that intrigue me. Um, One is, as you point out, these new metabolisms, that obviously don't use light. When we first think about the origin of life on Earth, which is speculative right now, obviously the earliest organisms probably used the different types of metabolisms, and they didn't photosynthesize, and so as we look at, and we can talk about what they might have done, but in order to see the kind of things that are done, you need to either go to the bottom of the ocean or go to these lakes and learn. Nature will tell us what, and those, so we may learn the origin of life on Earth by looking at these lakes as well, right? I think.
Yeah,
Do you think?
I think it's a great mirror what you're saying. Looking at the bottom of the ocean also gives us insights as well. And so, the more we understand about these extremophiles, these creatures
Mm.
living in inhospitable environments, the more we know about what life can do on our planet, and that might give us an image about what life is doing on other worlds,
Those planets.
and what to look for. Because we're going to need different tools to look at life. If we can't send a probe, we're going to have to use our imaging technologies. And so what can we get from imaging technologies that might, from like things like the Webb Space Telescope or other things, that would give us an indication that life exists on a body. And I think it is these natural experiments that have been done over millions of years on our planet that we still don't even know much about, and
Yeah, and
hopefully,
that's, we don't even
can.
know not much about life on our planet, and so when we make claims about life elsewhere, it's we have a lot to learn, and I
Yeah,
think
I
one of
mean,
the
I
best
think that's
ways is
you
to
work in the
study our
polar regions.
planet.
That's what it tells you. I mean, polar
Yeah,
regions are telling you we just, we don't even know what's going on to the ice there.
yeah,
So we
no,
don't even
we
understand
have
ice.
a lot of studying to do before we can
Yeah.
accurately say what's out there and looking inside. I just want to ask you, my own feeling is that when you see these microbes in lakes, I mean, I'm incredibly optimistic that life is teeming in the universe, not intelligent life, but But I'm wondering if you get the same take. It seems that
Oh, totally.
life can just arise wherever it can arise.
Yeah, I think, kind of life might be easy to evolve. I think conscious life, not so much. I mean,
Oh yeah,
it
four
took almost
billion
4
years.
billion years to happen on our planet and a lot of contingent events, but life itself, um, however you want to define it, you think about it, it arose. There's some evidence that suggests that the earliest life on our planet was probably 4 billion years, maybe
Yeah.
only 500 million years after the origin of our planet and the origin of the solar system
As
itself.
soon as the laws of physics allowed it to, but after the early
Boom.
late
Yeah.
bombardment ended and life arose within 100 million years of that, it seems to be really easy.
Yeah. So once you have the physical and chemical opportunity for life, boom, it happens, So that's why I'm thinking, yeah, it's probably abundant. And
So you agree with
yeah,
me? I'd make a bet that if we go to Enceladus or Europa and drill down, I wouldn't be at all surprised to find life there.
I'll be jumping up and down like a 9-year-old, but
Yeah,
yeah, I'd be, yeah. But yes, I
I want
wouldn't
to
be
be
highly
around
surprised.
for it. We'll see if we
Yeah, exactly.
get to it for that discovery. Um, and we'll say why, and later on we'll talk about why that's people are, especially in this administration, are fixated on Mars, in my opinion, inappropriately. But uh, uh, I'll be much more excited to go to Enceladus and Europa for reasons we'll get to. But anyway, okay, microbes are one thing. That's fine. You have a wonderful statement in the book somewhere, and I happen to have the page noted. You said on page 50, everywhere we look for viruses and ice, we find them. Now, that sounds scarier. Microbes sound okay. Viruses sound
Yeah,
scarier.
they do. Yeah, exactly.
And should we be worried? So the point is that if there are microbes, there are viruses, and if there are large regions that have been out of touch with the modern world for hundreds of thousands, if not millions of years, and there may be viruses that are ancient, should we be worried?
Yes, I wouldn't stay awake at night worrying, about it, but I would definitely think it's one of the things with climate change that can really impact us. Look, we know when permafrost melts, it can release microbes, i.e. anthrax, which can cause
Yeah.
infection. So you can have ancient infections that reemerge, like in Siberia, we've seen that. We've seen human fatalities, where the permafrost melts, you have an old corpse that was infected by anthrax, and it infects human populations or reindeer populations or whatever. Now, a Canadian team, a team from Ottawa, was working in Lake Hazen, which is in northern Ellesmere Island, about a decade ago. And they sampled the waters from the melting glaciers there, and they looked for the signatures in those waters, the chemical signatures of viruses. And they found numerous viruses there. In fact, they found numerous viruses that are known to infect animals. And we know that viruses can be reanimated after, or if they're alive, we're calling it reanimated. They can become active again. Animated seems that they're living, and it has a lot associated with it. But that they can cause infections, 50,000 years after being frozen in the ice. So yeah, so you have the predicate for that, but you couple that with a couple things. So with climate change, you have the melting of the ice, which is releasing these viruses and other microbes. But with that warming, you have southern species moving north. So you now are setting up the mix where, you have novel species heading to the polar regions, from the south to the north, and you're exposing them to new microbes that are the older microbes that are being newly exposed by the melting ice. You have the possibility for infections. Now, what would those infections be? Would they be something that would harm humans? I think we're a long way from that to some extent.
Yeah.
But there's definitely that's the mix that I think is of concern for the melting of the ice. The ice is like a vault that holds a lot of things. When waters freeze, you have everything that was in the atmosphere and the world gets caught in that ice. And so when it melts, you're getting these ancient denizens of our world that are re-entering, So no, it's cause for concern. But I wouldn't yet worry too much.
Yeah. Well, I think it's worth raising that issue, obviously.
Yeah, exactly.
And the point, and we'll get to other impacts of the melting ice in permafrost, and it's not just viruses that maybe we should worry us. But taking bigger animals, I mean, I love this stuff. As a non-biologist, it's always fascinating for me to learn. So yeah, there's strange microbes and new metabolisms, but I love learning about these strange animals too. And what biology can do never ceases to amaze me. I dropped biology in high school, by the way, when I was a kid. My mom wanted me to be a doctor, but I took high school biology, and it was memorizing the parts of a frog. And it's just like early and before, DNA and all the other things were. And so for me, it was just the most boring thing in the world. And so that's when I decided not to be a doctor. But since then, I've discovered, I mean, what we've discovered about biology is amazing. And not just genetics, but I love these things when you talk about these animals and what life can do, in particular, what life can do on larger scales, not just microbes, but
Exactly.
larger scale, adapt to polar environments. And I would be remiss if I didn't raise the woolly bear
Oh,
caterpillar.
thank you for doing that, Lawrence. When people ask me, like, what is my favorite polar animal? Like, is it a polar bear? Is it a penguin? I say, no, it's a little caterpillar. It's a little ball of fur that's about an inch long. And it's just an amazing creature. And
Yeah.
one
Talk about.
that, yeah, I mean, I remember, seeing one for the first time. I wasn't really prepared for it because it's just a nondescript little, brown black caterpillar. But they can be 7, 8 years old or even older. That can be that can be an elder statesman, that little thing on the. So
Yeah.
we're very careful to where we set up our tents, not to disturb these animals, because these little caterpillars can be really old, and they have an incredible life cycle. And this is what's special about them, and what enables them to have this life cycle is they spend about 4 to 8 weeks every summer when it's warm in the Arctic. They feed voraciously and feeding, and they have they fur on the outside, so it's sunny a day, 24 hours a day. So they're they heat up pretty nicely because they're dark and they absorb the light of the sun, and their hair holds the heat in, and they feed voraciously and they store all that. And so the summer is a time of eating and storage, and then winter comes along and they freeze, and they're frozen like a little frozen cylinder, and then they thaw again and they feed another summer in store, and then they freeze again, then they thaw and feed again. And so they do this feed, freeze, thaw, feed, freeze, thaw. They do that for about 6 or 7 years, all of that. And then in 1 year, once they've stored enough energy, then they metamorphose into a moth for about a week, find a mate, reproduce, and die. It's like 7 years of freezing and thawing and feeding until you fly around for like a week and have your fun, and then boom, you're gone. And so yeah, it's not crazy. And the way they do this is even crazier. So they have the fur, they have the life cycle, but then in their bodies, like a lot of polar animals, they have an antifreeze protein which keeps them when they're in that.
Is what amazes me.
Right?
Yeah, sorry.
So an antifreeze protein doesn't make sure that either ice crystals don't form throughout the body, so they don't freeze solid, or it keeps the ice from destroying the cells. So you have these specialized proteins in their body, which prevent the ice from having a form of frostbite, of caterpillar frostbite, and so. And then those antifreeze proteins are actually really special, because typically what they are is they're modified other kinds of proteins in the body. So they're simple modifications of other normal proteins in the body. So they're not invented out of whole cloth.
Yeah.
They're like tinkered and jury-rigged and repurposed proteins that do other things in the body. But other creatures have these antifreeze proteins as well. There are a variety of fish, there are varieties of worms.
Mm-hmm.
So antifreeze proteins are seen both in vertebrates as well as invertebrates. And they're often a strategy to avoid like what we get, which is frostbite, when you get that frozen skin. So it's incredible. I mean, incredible. And then the woolly bear caterpillar.
I mean, I've never heard of, and yeah, I mean, antifreeze proteins were novel for me. And the fact that they're so ubiquitous in many ways, it's just the fact that, biology makes antifreeze, just, I love it. But now there's another
independently a zillion times too. I mean, it's, it's not just once, it's not one off, it's lots of,
Yeah, exactly. Anyway, and the little I loved it. We told the story beautifully. This little frozen caterpillar just freezes. Boom, it's frozen. And it just sits there, and then it unfried freezes, and it does it a whole bunch of years just to have that 1 week of boom before it dies. Oh well. It's a nice week.
Yeah, exactly.
But the other thing that fascinated me, again, it's not biology finds many different routes, and some are convergent and some are not. And I was equally fascinated by this desiccation. That there's two ways. Obviously, you want to worry about freezing, as you point out, because it'll destroy the cells, because ice expands, and then when it contracts, it's water and deforms cells and breaks them. So you want to have antifreeze. But the other way is to get rid of water. And when you talk about that, there are other
Yeah.
organisms basically even become glass, right?
Yeah, exactly. They become a kind of a glass. And so so when you think about Antarctica is super cold, but because it's so cold and usually at high altitude because the ice is so thick, it's also super dry. So, so the risk in Antarctica is you can have both cold and dry, and that neither one of those environments, and particularly together, are conducive to life. And so animals, we talked about the antifreeze proteins, but as you mentioned, there's the desiccation threat. And so there's a species of worms. In fact, these are seen in other creatures as well. It's actually not a rare strategy. It's convergent, as you mentioned, that they make a form of sugar. It's called sugar called trehalose. And the trehalose, as they desiccate, as the water leaves their body, they make this sugar, trehalose, and it binds to cells and prevents them from suffering damage due to desiccation. And so what that does is they trade the water for the sugar, and that changes them into a solid. You can shatter them like a glass. Hit them, ting, they break in 1,000 pieces. And you don't want to do that. Come on, these guys are like, they're trying to live, right? Anyway, so but they would if you did. And then when it gets wet again, on the rare times it does, then the water replaces the trehalose, and they wiggle away. It's crazy. So turn into glass, hard, and then when it's dry, and then then when water comes back, they thaw out, and off they go. They're back into the races. Life is doing incredible stuff. You have these antifreeze proteins, you have these trehaloses, these sugars, and you're seeing evolution coming up with multiple ways of getting there. It's very inventive and creative.
Yeah.
And we can trace the ways they did it biochemically. It's not like they're invented in whole cloth. They're modified existing things. Yeah, I mean, it's just there's a whole world of science and understanding these adaptations.
Yeah, the fact that when again naively you think of water as an essential part of life, and you've got these animals that for a while don't have water. They're sugar. They're glass. They're like really Star Trek aliens. The rocks. The famous one of my favorite Star Trek aliens is a rock.
The Horta.
Yeah, Horta. You got it.
I've until I gained some credit on this one.
You got credit. You got straight. Yeah. But anyway, it's I guess that's the point, and that was my point when I wrote the Star Trek. You don't have to go to Star Trek to find weird things. The real world.
No, exactly. No, right. The real. It's like what Richard Dawkins says, right? The magic of reality.
Yeah, exactly. And so, that was the conceit of that particular book of mine. But anyway, the other aspect, so that's fancy stuff, and it is amazing, and I love reading about it, and I love giving me a chance to talk about it now. There are other stuff that I love as a physicist. Everyone always says I make these things about me, but anyway, I'll get those complaints now again.
It's your podcast.
I wrote a book, Fear of Physics, where I began talking about simple physics and scaling, and how you can learn a lot of biology just by scaling without knowing any biology. But one example I didn't use, which I'm going to use from now on, is the wonderful fact when you talk about even bigger animals that physics governs the shape of animals in the polar region. Just simple physics. Totally. I'll let you explain it.
It's the famous surface area to volume relationship.
Yes.
So you lose heat based on surface area. But volume, your mass, is basically what you're conserving heat with and producing heat with. And so it's so surface area to volume is really critical. But as you scale upwards, obviously, you have properties that change at different rates. So one of the sequelae of that is, as animals move into polar regions to conserve heat, what they typically do is reduce heat I'm sorry, excuse me. Let me reel this back a little bit. Sorry, Corey, we're going to cut this again. So basically surface area to volume relationships really control heat loss in a lot of ways, and heat gain in many ways. And so when animals, migrate into polar regions, we typically see them evolving new kinds of body shapes that conform to the physics of the situation. Typically what they have to reduce surface area, which is a way to lose heat, is they reduce the size of their appendages. They tend to have smaller appendages. They tend to be relatively larger than the than the southern species. So body shape conforms to the physics of heat loss and heat gain very nicely in terms of those proportions. Pretty remarkable. And it's one of those things you see in different lineages. You see it in foxes, you see it in bears, you see it in different kinds of critters. It's not just a one-off. Seems to be a general regularity. And in sorry?
Governs. As a physicist, I love when physics governs things. The simple fact that area goes like r squared and volume goes like, and therefore mass goes like r cubed, means the bigger you are, the more mass you have for volume, and that's you see big animals, and you want to make sure you have
tiny little limbs. Yeah, exactly.
Yeah, and it's fascinating that that you can, from very little, can get so much, and when it comes to
it's and there's a whole science of that, and in biology these regularities are called laws. They're Birdman's rule or law, and Allen's rule or law. You learn about them in intro bio. These the physical regularities of body shape as creatures migrate into northern regions.
Well, there's two other things briefly I want to talk about before moving on elsewhere, and I'm aware of time, but there's so much to talk about. One is I think I was going to talk about the turtle clocks, but I think I'm actually, which would allow us to go in a lovely segue about people going insane. But I think I'm not going to go there right now. I'm going to.
Just want to talk about insanity.
Well, one thing that was interesting to me, there's the different kinds of fat. Why don't you want to talk about that a little bit? I found there
are different kinds of fat in the body, and one of the discoveries in the last, say, 5 decades is really understanding that fat is not just often an inert tissue. It's a tissue in our body, and it's a living thing. Fatty tissue. Yes, it provides it provides insulation. When you think about the insulation of the body, it's important to have, particularly in these regions, sufficient insulation around your organs. But some of this fat actually can produce energy, and it's called brown fat. And brown fat contains mitochondria, and those mitochondria, can actually burn energy, can create heat. And so brown fat is typically seen in polar creatures. Brown fat can be stimulated to form in humans that are in colder environments. And brown fat is not only an insulator, it's a heat generator. So brown fat is a good fat in many ways, and it actually increases your metabolism, increases your heat. And fat is not one thing. There was an experiment done in Australia of humans where they put them in rooms and kept them cold for 6 months at a time. And they measured their fat, and it turns out they were able to produce brown fat actually started pretty quickly, after a few weeks to a month of starting the experiment. So
yeah, that's great. It's like cholesterol. There's good and bad, and there's good, bad, and bad fat, and brown fat and white fat. Yeah.
Well, yeah, and if you want to lose weight, the best diet program is camping in the Arctic, because you're cold all the time. The type of fat you produce changes through spending a lot of calories just living up there.
Now, there's a money-making scheme to support your science. Just take fat camps in the Arctic. That's
Shubin Industries. There you go. We're going to start a new corporation.
It may not get any federal funding. Anyway,
no, exactly.
But
I'll need it.
Okay, let's jump to the other area, which is an area I have had a personal interest for a variety of reasons, but also scientifically. And that's meteorites. And I used to tell people, when you want to look for meteorites, you go to Antarctica. Why? And people come up with all sorts of ideas of magnetic fields of the Earth and everything else. I say, no, because it's white. And you see a rock on the surface, it came from up there, and unless it's in a mountain. I mean, and of course that's true to some extent, but in fact, not quite true. One of the things I should preface this, because I almost got to go meteorite hunting in Antarctica, because I was the chairman of the physics department at Case Western Reserve, and my colleague Ralph Harvey over there in geology was in charge.
He's the guy,
You mentioned him in your book, and I desperately tried to pull rank somehow to be able to get on that mission. And in fact, you talk about how wonderful it is and how democratic it is in terms of in the book. And I'm an example of that, because the fact that I didn't get to pull rank to go to Antarctica is an example of the fact that it's really a democratic decision of getting people to. I mean, because I don't know how to say this right. I mean, the reason I thought I could do, let me put it in this context, is it doesn't take a lot of skill, right? Because you're zooming along and you can, and yet it's pretty obvious if, what's a meteorite there. And I mean, obviously you have to be trained, but, it's actually, and that's why I thought I could do it, but it's actually a little more different than I thought. I'd always thought you're just zipping along these plains of ice, the surface of the ice, and you see a rock. But in fact, actually, the meteorites accumulate, and there's a strategy of
Yep.
accumulation. So I want to talk about that a little bit.
Yeah, I think that's what sort of got things going. Really, was
Yeah.
that. Now you can find meteorites that way. You can zip around, see something dark on the
Yeah.
ice, and pick it up. In fact, that
Yeah.
people have found them that way. But more often than not, it was the realization by Japanese teams, and in the early days, Americans as well. But began with the Japanese. They discovered this one spot, the Yamada Mountains in East Antarctica, that had a collection of
Yeah.
like 9 meteorites, and they were nearby each other, but they weren't from the same meteorite fall. They were different meteorite falls, and they were different kinds of meteorites. So it means that the meteorites collected in that region for whatever reason, and it all comes back to moving ice. So the ice, as I told you earlier, is moving from more or less the center of Antarctica towards the coast, along these rivers that are going a kilometer or two a year, right? And what happens is when that ice moves along and hits a mountain range, these are mountains that go pop through the ice. What'll happen is the ice starts piling up at the base of the mountains, such that what happens is the ice starts to convect upwards. So ice from the deepest parts of the ice sheet start convecting upwards at the base of these mountains. So when you look at the mountains of Antarctica, at the base of the mountains is the oldest ice. This is ice that could be, 1 million years old. It's the famous blue ice. It looks very different. It's not white, it's blue. And it's because it's really dense. You can't break it with your hammer. If you start sliding on it, you can't stop because it's frictionless almost. It's crazy. And so you have all this ice moving towards mountains, and then it convects up. And so everything in that ice starts piling up at the base of those mountains, from all depths of the ice. And so think about this. If meteorites are hitting Antarctica at some small but constant rate, but you have this mechanism that conveys and collects all the ice at the base of these mountains through multiple layers of time, over time, what you're going to end up with, if you have the right conditions, is a collection of everything that was in that ice, including those meteorites. And so what they do is the meteorite hunting team looks for places where you have this blue ice that's convected to the surface, usually at the base of these mountains. And then they go and they, pop, 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 pick up the ice. And pick up the meteorites. And they found, I think, since the project began in the 70s, they found about 50,000 of these meteorites.
Yeah, it hadn't
crazy.
occurred to me that strategy, and I was, although it is true, as you say. I mean, you see pictures of these meteorites on the ice sheet.
You will find it that way. You could, and people do.
The first one, I think, in 1912, you point out, was just someone wandering around, and I thought the
air
Alan
tractor.
Hill, I think the famous meteorite that I want to talk about in a second was also Alan Hill's meteorite, but
that's the base of the mountain. Yeah.
But but I want to point out something that made me think about it. I used to think, well, of course they come from up, but then as a physicist, I was amazed how stupid I was, because meteorites are coming at a pretty fast velocity. They don't just land on the ice. So in fact, some of them end up on the surface like that. But one of the reasons you want to go to those convecting regions in the blue ice is that the meteorites penetrate. And they go down.
Then, exactly.
And that's why. And so, that obviously, that's the point. You want to go to the point where they broad, because most of the meteorites have penetrated down, and you won't see them on the surface because they're impacting with such a high velocity. And I slapped myself in the head when I realized that upon reading your book, that of course you want to go to where they're brought up, because most of them are deep down.
Exactly.
Anyway,
exactly.
And then there are two types, as I point out. I mean, some of these, of course, the chondrites are come from the origin of our solar system, 4.56 billion years old, earlier than the formation of our solar, and they're fascinating to look at for those reasons. But what was the big surprise, I think, and I remember it vividly from 1996, I think, but was the realization that if you want to find bits of Mars, you don't have to always go to Mars. You can, and was a realization that material is exchanged between planets, that no planet is an island, and the
Right.
realization that I mean, it wasn't first. You pointed out, I think it was in Egypt when meteorites were found, which were very unusual composition. And of course, it wasn't until we went to Mars and looked at the composition of Martian rocks with our missions that had gone to look at them that we realized that the composition was exactly the same, and that you can get rocks from Mars and maybe somewhere else, and the moon and everywhere else here on Earth. That's a fascinating discovery.
Yeah, and you don't have to run an expedition to Mars to get these rocks. You just have
Yeah.
to support polar research and people in snowmobiles and going to the right places. Yeah, and they're relatively, they're not the chondrites, as you mentioned, are the most common kind of meteorite. But
Yeah.
the Martian ones are there. And yeah, I think that was a big surprise to people. The Egyptian meteorite famously vaporized a dog when it hit it.
Yeah. I don't know if it really vaporized a dog, but
Yeah, I
it
don't
did.
know.
They
It's
killed the dog. I mean,
apocryphal.
I don't
Yeah,
know.
exactly.
Yeah, I think that might be
It's
a little bit apocryphal. But yeah, and you pointed out how sad it was. Traveling for could be bouncing around the globe for hundreds of thousands of years, and then zooming in. That poor dog was in the wrong place at the wrong time.
yeah, exactly.
And-
Yeah, exactly.
But this one meteorite became famous, and it was in the White House, as you know. I think Allen Hill's ALH 84001, because it was analyzed, and I was almost I thought afterwards it was trick photography, because these small structures were seen that, if you looked at them, looked very much like the oldest fossils on Earth that are 4 billion years old from
Oh,
Australia.
totally. They're
Yeah.
just a lot smaller. Yeah.
But I think we were fooled. Man, you could tell me if I'm wrong. In retrospect, I realized we were kind of fooled, because they look like them, but they're about 40 or 50 times smaller.
Yeah, they're a
And
lot
therefore,
smaller.
and that was to me, that's the Achilles heel, the fact that there are plausible non-biological ways to produce such things.
Yeah, I mean, but how you talked about before is we don't really know what to look for life
Yeah.
on other bodies. I mean, so I talked to people who think about these things, think about Mars surface, things about meteorites and so forth. And oftentimes people say, we really just don't know. I mean,
Yeah.
it's unlikely it's a living form based on what we know, but we can't exclude it, right? I mean, just because it just shows the gap in our knowledge. I mean, yeah, it's likely formed by an abiogenic process, something with the something with the lithography, with the formation of the rocks. But you can't exclude. I mean, nobody's like sort of debunked it, because you can't, because we just don't know enough about what life might be. Maybe
Yeah, the
you
point
could
is, it could have been life. But I think the old claim of, Sagan borrowed it from other people about extraordinary claims require extraordinary evidence.
Yeah, that's exactly right.
Clinton in the White House got, it's a very exciting moment saying we discovered life elsewhere. And the point is, yeah, maybe life, but in science, it's got to, if you're going to make an extraordinary claim that it is life, you better, you can't say, well,
you're
it
gonna
might
need
have.
some, you're gonna need a lot more than just a few rods.
But what it did do was at least for me, and maybe for people who thought about this, it wasn't such a big change. It changed everything by realizing that no planet is an island, and that if you want to,
Right.
and because the early life on Mars may have been hospitable to life early on, it's certainly possible. I wouldn't say not plausible in my own opinion, having thought about it a lot, but possible that life originated on Mars and then later on polluted Earth. Because what we've learned is that microbes, as you point out, and extremophiles can survive in exotic environments for hundreds of thousands of years, if not longer. And it's plausible that a life form that arose on Mars could have been knocked out and ended up on Earth and polluting the Earth. So if you want to know what Martians look like, look in the mirror, maybe.
Yeah, I mean, I would agree with you. Yeah, I would say it's plausible, but not probable, improbable.
But the more important thing, as a person who taught me a lot about this when I was writing a book about an atom, the life history of an atom, my friend Andy Knoll, who you probably know well, and
of course, it's fabulous science.
And Andy's at Harvard in the Organismal biology department. He's pointed out to me. He said to me once, and that's the key point. If we find extinct life on Mars, the big surprise will be if it isn't our cousins, because of that exchange. And that's the difference between looking for life in, say, Enceladus or Europa, which has been separated from the environment by an ice sheet,
Oh
and
yeah,
Mars,
for billions
where
of years.
there's been exchange. So do you buy into that? If it's most likely, if we find any evidence for life on Mars, it'll be difficult, unless of course it has a different kind of DNA and all the rest, which is, I think, highly unlikely anyway. It would be difficult to say that it isn't our cousins.
Yeah, and if we find a creature that clearly had some sort of nucleic acid, that is, similar to the nucleic acids on life, I'd say the default hypothesis is that we've traded,
Yeah.
material early on the history. And, we have these asteroid impacts, they send ejecta and all.
Yeah.
And the material goes off to the races and lands on another body. No, I think if we find nucleic acid based life form on Mars, I would think the working hypothesis might be that somehow there's been an exchange.
Yeah,
And that'll take phylogenetic analysis. People have to look at the sequences and use some of these deep branch phylogenetic methods to really test those things. Whether you can or not, I don't know, but we'll see.
Yeah, we'll
We
see.
should be lucky enough to have that. Let's be lucky enough to have that.
Be lucky enough to have that worry.
Yeah,
Absolutely.
exactly.
But I have a bet, which I'm happy to lose with Richard Dawkins. But I having thought about this, I'm almost convinced that life found a unique way to exist. So my own feeling is, if we find nucleic acids in life in Enceladus, any life we find on the oceans and Enceladus is likely to be a second genesis of life. So it's
I would think so.
That's for sure. But I'm betting, and I'm happy to make this bet with you, and I'm hoping I'm alive to lose it if it is that way. I tend to think I wouldn't be surprised to find that even if we find the second genesis of life on under the oceans of Enceladus Europa, that it will basically be DNA based and have ATP and more or less the same biology as us, because I think life found a way to work. But do you think I'm being naive here?
Yeah. No, I mean, I'm actually, you're not going to get a bet out of me, because as I get older, it's not that I would bet if I disagreed, but I actually kind of agree with you, because as I get older, I move less from sort of evolution is a pile of contingent events to more of the fact that the physics and chemistry of certain situations constrain the range of possibilities of the outcomes that can happen. And that what we see is probably in the history of life on Earth, we probably had multiple inventions of life on Earth. It didn't probably just happen once. It had probably happened multiple times, when the slate wiped clean and you had different origins in different places. And, I'm thinking, you probably I know for a fact you followed, physics, the rules of physics and chemistry, to have that life. And I think in all those cases, we've had nucleic acids. So I would be an argument that, we're probably looking at sort of constrained possibilities because of physics and chemistry. Yeah.
Yeah. I mean, it constrains things, and life has found a remarkably way to maximize the opportunities provided by physics and chemistry. And it found a really good route, and it works. So yeah, if it ain't broke, don't fix it, I guess. And so okay. It's interesting that your feeling is the same. I think it
may not look a lot like our DNA or RNA, and maybe, in fact, it probably is like RNA based or something like that. I mean, if I had a bet, and that aren't those RNAs may be very, we know our own RNAs can be very, very highly variable. So I'm thinking it may be some kind of RNAs. Maybe it's some kind of RNAs that we can't even imagine right now. But it might be some.
But people have argued. Well, I don't want to push this too far because but I will push it a little bit because that's the way I am. Not all. There's some subset of amino acids that we use in some, and the nucleotides are some set of possible nucleotides. And people have said, well, maybe there'd be other nucleotides. But I'm willing to bet even down as far as the choice of amino acids and the choice of nucleotides, all of that is governed by chemistry. I think a fundamental energetics of chemistry, and I would be surprised if there was that much variability. But anyway, now, okay, going back to some of the discussion in the book that I want to really hit, especially as we get near the end of this, and for your sake, I want to let you know we are getting near the end. Probably one of the most important things that you can get out of the book in general is the fact that the Earth is dynamic, the ice is dynamic, the history of the Earth shows dynamic things, and that the way things are now is not the way things always were or the way things always will be. And there's lots of great discussions. And I know a lot of that has been learned by looking at ice. When I was in Greenland, I did the study of the science, and boy, so many things have came out of that. And you talk about Fridtjof Nansen and what he learned and ice cores. But even Alfred Wegener, the guy who first came up with continental drift, was in Greenland. It's really, but one of the things that is interesting to me that you point out, and as we talk about slow and rapid change, which is really where I want to head, is that there was really no ice on the Earth till about 2 billion years ago. Again hadn't really hit me till I read it in your book, and I mean it stands to reason, I suppose, in some sense. I assume. Tell me if I'm wrong here. I'm assuming it's largely because the early atmosphere of the Earth had huge amounts of carbon dioxide, and thousands of times more than now, which stopped it from being frozen because, after all, the sun was 15% less bright then.
Mhm.
But I guess I was surprised that ice arose 2.2 billion years ago, and that was before the period of great oxygenation, I guess. So
Mhm.
what was it about 2 billion years ago that caused ice to begin to form on Earth?
Yeah, so what we have is there's a mix of things. And I think the formation of ice on our planet is kind of takes a perfect storm of events.
Yeah.
There's things that are happening to the atmosphere, things that are happening to the dynamics of the Earth, things that are actually happening with life. And it's the interplay of
Mhm.
all these three things. And what you have are these cycles in the movement of the continents. You have periods of times where the continents come together, periods of times where the continents break apart, again, periods of times where the continents come together again in a different configuration, and they break apart in a different configuration. So we have these supercontinent cycles. Supercontinents form, break up, form, break up. And the distribution of continents on the planet can affect the global climate in very big ways, because it affects the amount of ocean, the distribution of oceans, the distribution of land masses, how heat is absorbed by the Earth. So that's
Yeah, the
one
albedo of the
factor.
Earth, in fact, very
Huge
important.
factor. Exactly.
Mhm.
And then what life is doing is also a big factor as well. I mean, so life produces, as an outcome of, of energetics and metabolism, life produces a variety of molecules as waste products. It's either oxygen or carbon dioxide or other products as well. So that will change depending on what life is doing. That can change the context of the atmosphere as well. And you have all these factors coming together, and there are moments of time where the Earth is absorbing more heat than it's releasing, and you have warm periods, you have cold periods, and so forth. But a lot depends on not only the amount of heat that the Earth is storing based on the distribution of the continents and the distribution of oceans, but how that heat that the Earth has moves across the Earth. Ocean currents can change, and ocean currents don't just take nutrients and things; they also carry heat and salts from one part of the Earth to the other. Long way of saying that when you put all this mix of factors together, there are periods of times that promote cold, and there are periods of times that promote warm, cold, warm, cold, warm. And those cold periods can give rise to moments where you have ice either covering the poles, covering both poles, covering one pole, or covering the entire planet.
It's interesting. That's a key point, that it's not just absolute temperature, it's the way it's distributed. You can have cold times
Mm.
where there isn't ice, and you can have warm times where there is, depending upon,
Exactly.
and and that there are drivers, as you point out, and we'll get to, I guess, that obviously the ocean current in the Atlantic that takes warm water and takes it up to the poles, and then that water sinks, and then that's driven. The energetics of that is driven by the salinity in a large way,
Exactly.
and it's out. Um, that changed when the continents changed, because when the Pacific and Atlantic were connected, when North and South America had a gap between them, the salinity was of the Atlantic was very different. But once that gap closed, the salinity of the Atlantic changed, and that drives that ocean current that now determines not just the snow in the Arctic, but also why Europe is much warmer than at the same latitude than North America.
Exactly. And that's the example I mentioned in the book, but to show essentially that the distribution of the continents can affect these circulation patterns of heat. And so tectonics and continental drift is intimately tied to long-term patterns of climate. And yeah, that what you're talking about there with the Atlantic Ocean becoming more saline over time as it became separate from the Pacific, that drove that current ever fast, made that fueled the current to become ever faster, which pushed obviously snow and moisture to form at the North Pole.
Yeah, no, and also even I remember when I first heard about Snowball Earth, it was from then a young guy, Dan Schrag, who's now older, and worked with Paul
Aren't we
Hoffman
all?
yeah, and one of the key there was a time which is amazing, and it was pretty controversial when it was first pointed out, when the Earth more or less froze over, and partly it was due to the fact that there was a supercontinent and its location near the equator. That changed the albedo of the Earth, that initiated that whole context. So the continental this interesting interplay between the oceans and continents is important, but it does mean that there's been a lot of change and over geological time, but we'll also learn that there can be changes over quicker times. But I think one of the things that you mentioned, which is surprising to me, is that the polar ice caps have only been a feature of our planet for 10% of its existence. Therefore, for 90% of the time on Earth, there haven't been polar ice caps, and that's really so. We're really an anomaly.
We're living in a weird time. Yeah, a very weird time.
In a very weird time, and as we pointed out at the very beginning, or much earlier in the program, it was only 34 million years ago that ice started to form. That now forms, but even then, it selectively did it in different ways around Antarctica versus the Arctic. Again,
totally
for
different.
reasons. So maybe you can go over that a little bit, because I think that's fascinating.
Yeah. So we've been in, I think, in a trend of global cooling, actually, for about the last 50 million years. And that's, again, probably because of tectonic changes. I mean, the best hypothesis out there is that the rise of the Tibetan Plateau has changed global climate for the last 50 million years, because as that rises, that pulls, that actually forms a mechanism for rock weathering to pull carbon dioxide from the atmosphere. So great theory by Maureen Ramo of Columbia University. And it was controversial at the time. But I think what it shows is that we've been in a very special cooling period for a long period of time. And that cooling alone didn't cause the freezing of the poles. What it took were other things to happen. And we come into continental drift again. What changed in Antarctica is as Antarctica moved towards the South Pole, so it was originally up where Australia is today, and then moved further south to the South Pole, that set up an ocean that surrounds it, the famous Southern Ocean. And the tidal movement of the winds of the Earth and the movement of the Earth has created an ocean current. That is, if you've ever crossed the Drake Passage, I mean, it's ferocious. So you have this ocean current that basically spins around the globe, around Antarctica, and that current has actually insulated Antarctica. So as Antarctica was sitting at the pole, it had this current around it that kept the cold there. It insulated it, so it just got colder and colder and colder until it actually formed, and then wetter and wetter and wetter in many ways, and then it formed ice in the continent there. And that happened before the formation of the ice in Antarctica happened before the formation of ice in the Arctic, which is largely driven by, we think, by the Atlantic Ocean getting ever more salty, as we talked about before. But that happened about 15 million years after the formation of the ice in Antarctica. What's remarkable is, if you look at the fossil record of Antarctica, it was a tropical rainforest teeming with life about 60 million years ago. Teeming with life. Wow. And then when it went into the freezer, all the life's gone, pretty much, except for, obviously the fauna and flora we're familiar with today. I mean, just remarkable. And that happened before the Arctic, the freezing of Antarctica.
Yeah, and we'll go into a little bit more detail here, but one of the things I remember, what first jolted me about climate change, I was chairman for a decade or more. I was chairman of the board of the Building Atomic Scientists Board of Sponsors that determines the doomsday clock every year.
Yeah, you saw University of Chicago. Yeah, exactly.
Yeah, exactly. And I would visit there, and we'd have doomsday meetings, where I'd learn from experts about different things. And I remember the first time, I think it was Jim Hansen who I can't remember who showed this plot, but during these periods of global cooling, I mean, when you're dumping more ice, you're taking water out, and the fact that sea levels can change. And I knew about sea level change a little bit, but when you see the data, the sea levels have changed on Earth by not just inches, but by 100 meters over different I mean, it's not. This is not science fiction. Sea level can change not just by meters, but by tens of meters or more, and has changed over geological time by up to 100 meters or
Yeah,
more.
exactly.
It's
There's
amazing.
about there's about 150 feet of sea level change frozen in Antarctic ice, right? Antarctic ice. And when you think about that ice has come and gone, well, think about that how much the oceans and the seas of the Earth have changed, how that affects coastlines, how that affects islands, how that affects the weather patterns. It affects every property of the planet in many important ways, all across the planet.
And well, and then and we've learned about this a lot. What's great is that not only do we see this in Antarctica, but we use Antarctica and Greenland to some extent as a tool. And again, I'd be remiss if we didn't mention it. You mentioned Willie Dansgaard, but the idea that the Antarctica is a wonderful tool to look at the history of the Earth because the ice captures the Earth's history in two beautiful ways that I know of. You talk about one in the book, but there's another one too, I guess. Due to chemistry, that the realization that first ice builds up every year, so that deeper down you go, you're going back in the history of Earth, down back to, I think the oldest ice cores are now 800,000 years old. I think
A little older, actually, yeah.
yeah. I mean, the famous ones were 400,000, but now they go down deeper.
Mhm.
But trapped in that are fossils, not of animals, but fossils of the climate of the Earth. And I'll let you talk about it a little bit.
Well, think about what's frozen in the air. I mean, you have bubbles in the
Yeah.
ice that preserve the ancient atmosphere. You have ancient particles, soot, and others that are preserved in the ice itself. And we talked about the microbes that are in the ice itself. You think about these layers of ice as being a vault of whatever was in the air at the time, captured like a museum piece, if you will, like a time capsule.
Yeah.
I mean, that's what they call these things, time capsules. And um, it gives a window into what the ancient atmospheres were. It gives you a window into what microbes were around at the time. The soot gives you a window into what was happening with different parts of the Earth and air circulation patterns and so forth. I mean, you can really, once you know how to look, you can read these things to tell so much about what the world was like at that time.
It's amazing, and you can actually see the layers. It's like a tree if you actually look at
Yeah,
night.
totally.
And of course, yes, one of the things which is the first thing you realize is that these bubbles do tell you the atmosphere. So that's how we know what the carbon. When we have these graphs of what carbon was over back to 800,000 years, we can measure. We can literally measure the early atmosphere.
Absolutely.
The thing that's more surprising when I first learned about it, and you mentioned it also in the book, is it is also a thermometer. It tells us what the
Yeah.
temperature was, which is how we can know how carbon and temperature are related. And the thermometer is fascinating. And so maybe you briefly mention it.
Yeah. So basically, what they're doing is looking at different isotopes of oxygen.
Yes.
And oxygen exists in a heavy and a light form.
Mhm.
And that, so basically there's an oxygen that's heavy, an isotope that's heavy, an oxygen isotope that's light. And the ratio of the light to heavy form in a layer of water can give you a sense of what the temperature was at that time. Because they have different tendencies to evaporate or form in this, go to the gas or go to the gas or go to the solid. So what you have is you have this thermometer, which is based on the proportion of heavy oxygen isotopes to the light oxygen in the layers of ice. And you can calibrate that thermometer to known places where you actually know what the oxygen,
Exactly.
isotope ratios are
You
doing. So,
oxygen
so you can
18 is
get
heavier, and it'll precipitate out earlier. And if it starts to rain or if it's colder,
exactly.
as you go to those those higher latitudes, it'll precipitate out, and you'll see less oxygen 18. And it's really kind of amazing thermometer. And you
Oh,
can
it's incredible.
that to me was the big surprise. Not just that you could see the atmosphere, but you could actually correlate it to temperature. So we can check our physics and check that physics works, that there is a correlation between, say, carbon and temperature.
I mean, so you can get these records of the relationship between carbon in the atmosphere and temperature, through the bubbles, through the geochemistry of the ice.
Yeah.
And you can map them, and you can see over time for the last hundreds of 800 and 900,000 years, you can track how they go in parallel with one another. It's a very remarkable curve because they do follow each other very
It is.
precisely.
It is. But
Um,
that was in some sense one could expect that because it is physics. It's simple physics. It's not some fancy stuff. Climate change is simple physics. But what was surprising, and still is surprising, and will lead us maybe to present and future, is the fact that when you look at these things, you don't just see changes over geological time. You can see temperature changes over what we might think of as human time scales, hundreds of years.
decadal scales.
Decadal time scales. And there's evidence, I think 26,000 years ago or 20, I mean, there's a bunch of them. Rapid temperature change has been confirmed a bunch of times, and associated with that in decadal time scales or century time scales, rapid sea level changes. And though that should give us pause. So I'll turn it back over to you.
I mean, that was actually once people got these tools to measure temperature and carbon and evaluate ice by looking at ice cores, it opened up a whole new world to discover. And primarily starting in Greenland, but later in Antarctica, and particularly in Greenland, what was discovered in the north was just how fast this system can change. So there are moments where you had maximum ice in the history of the planet, but at those in recent years, I say 24,000 years ago. But what you'll have at these time periods are short intervals, maybe a decade to a century, where you can have a change in global temperature of about 7 degrees Fahrenheit, and then you can then you can find massive breakup of glaciers, and you see the climate change changing very fast, the quality of the ice changing very fast, and the changing of the sea levels changing very fast. So you're seeing sort of naturally events which can drive rapid changes in ice, sea level, temperature, and so forth. And these all happen before humans. And it just shows how sensitive the system is to perturbation. Changes in temperature can change ice, can change sea level. And it's not a system that is very stable. It's a system, and particularly in certain conditions, that can change, and that those changes can track very quickly. And that's empirical. That's purely empirical. That's just, you can show it just by looking at data.
That's the important point. It's empirical. You can't deny that. It happens, and it has happened, and it could happen again. And for those of us who've been in the West Antarctic, as I have in the ice sheet, as we look at what's happening now, there are scary things happening, and we don't have enough time to go through all the details of the fact that warmer water melts the ice, the ice sheets at the edge of certain parts of Antarctica that stand as bulwarks to glaciers that hold them back. And when those ice sheets are gone, the glaciers can more quickly flow into the sea. And if the West Antarctic ice sheet, which seems to be breaking up, does break up, then global sea level changes will be like 2 feet, right? Something like that.
In the past, it was actually about 14 feet.
If the whole sheet goes, but
the whole sheet goes is 14.
The whole sheet goes, you get 14 feet. Yeah, but just the even in the optimistic case,
the margins, So where you're talking, so basically what you're talking about is that as the ice moves from the center of the continent to the coast, where the most of the melting happening is at the coast, where warm waters of the ocean meet the ice at the margins. But the ice at the margins of the continent are like dams or breaks, bulwarks that hold that ice coming from the center of the continent from going into the ocean. But as the ocean warms, it melts these dams, if you will. And as they melt, then we can expect more ice to go into the ocean. And the West Antarctic ice sheet is the one I think is the one of most concern, because that whole area, the ice is sitting on rock that sits below sea level. So the ocean at the coast is not only just sitting at the coast, but it seeps between the ice and the land, going deep underneath. And that's warm water causing the ice to melt from below. And so there's concern that we could see several feet of sea level change in the coming century or two, based on what's happening on the ice in West Antarctica.
Just in that part of the West Antarctica.
Just in that small part. Yeah.
You do say, if the history of rocks, ice, and genomes is any guide, our future will be one of rising seas. And it's not gloom and doom to suggest that rising seas are happening. It's not just it's not a future where the seas are measured to be rising by millimeters per year, but nevertheless at a measurable rate. Um, and this hit home to me, and that's why I wrote the book on climate change, because so much of the population I was in the Mekong in Vietnam at the time, where almost all of South Vietnam is less than 1 meter above sea level, and so one can make projections. And you're right, projections are variable, but the example I like to use is of Clint Eastwood in the Dirty Harry movies, where he points this gun at a guy and says, I don't know if there are any bullets left. You feeling lucky, punk? And I kind of feel the same way about the planet. Are we feeling lucky or not? And if it seems to me, while it may be speculative that large sea level change can happen in centuries, if there's that possibility, shouldn't we? The fact that there's uncertainty, it seems to me, should make us more worried than the fact that there isn't uncertainty. Namely, if worse things can happen, then maybe it behooves us to try and think about how to make sure they don't, even if it's just a small possibility.
Yeah, what's certain is that seas are going to rise. There's just no doubt about it. I mean, it's already baked into the system. We can see that. You talk about remote sensing. We're seeing that we're losing 240, 280 gigatons of ice per year from Greenland.
It's accelerating.
And Antarctica. Yeah. So an enormous amount is going into the ocean, and that's just not disappearing. It's going to it's raising sea level about 1/4 of an inch a year, and that's accelerating. Yeah. And so, so the question is really, yes, we know it's rising. But the question is, how much will it rise, and how resilient could we be to whatever rise that happens?
Exactly.
Right? Those are the two unknowns, which we really don't know. You have estimates of sea level rise, some of which are not particularly scary, other ones which are truly scary. You have estimates of human resilience, which none of them really come out too well, because what we have is most human populations are along the coast. We have trillions of dollars of value along the coast. Not only do we have Pacific Islands, whole island nations that would disappear, but we also have, as you mentioned, whole communities, whole nations that are below sea level. But there's also other things that happen with changing seas. That is, as you change seas, we've talked about global circulation patterns of ocean currents. Well, that changes climate patterns.
Yeah.
We have whole societies, geopolitical boundaries that are based on coastal margins, but also having certain climate patterns with agricultural belts and habitable zones and so forth. What we're doing is we're setting up a world of really a lot of uncertainty. And that uncertainty starts with the amount of carbon that we're putting in the atmosphere. And it's hard to predict the future, but I can tell you right now that I can guarantee you we're going to have rising seas. I can guarantee you it'll cause changes which we're going to need to adapt to, but we just don't know. The problem is we have no idea, really kind of to what degree we can adapt, or what degree we'll have to adapt. I can promise you there'll be some degree of adaptation, but it could be a lot, could be a little. I don't know.
We can adapt, and that may be what's required, because we're not showing any evidence of stopping what we're doing. We'll need to adapt if we're. But one, I was surprised. You say one somewhere you said that one prediction was only 4.5 inches sea level by 2100. I don't see that as here.
Yeah,
let me just give you the physics argument. We've dumped enough energy. Water, when you heat it up, expands. And the oceans haven't thermalized all the heat we've dumped in the last 40 years. If you just talk about that heat that's already in there, when that thermalizes, that's going to produce 1/4 of a meter increase in the sea level. That's built in. I don't see how it could ever be less than that, because of just the fact that heated up water expands. But forget the glaciers.
Yeah, that particular estimate. So basically, there was an issue in Nature. It had 2 papers in it back to back with different predictions about what would happen with Western Arctic melting. And one was truly scary, at several feet of sea level change in the next century. Now, the other was like 4 inches or something. And both of them were trying. One of them had an estimate that included kind of the what's likely to happen with the margins, those ocean cliffs, and how they're more likely, and as they erode from beneath, how they're more likely to collapse catastrophically, which gave the larger estimate. why you might have smaller estimates is really about the dynamics and uncertainty in the dynamics of the ice. And I agree with you, it's the less likely of the two scenarios. But there are two things happening. As you lose ice, the land itself rises up. So
Yes.
based on that, you kind of don't know. And the other is, as ice breaks apart, you really kind of don't know what the dynamics will be in its pieces, that it could be like forming clogging zones, which hold that ice from the land back. We just don't know the dynamics of that situation. And part of it is that, everybody thinks they understand ice because, you see it in your class and it's in a drink or whatever, and it's the most simple of substances. But the reality is once it gains large size, the size of the state of Florida or the continental United States, it takes on properties and complexities which are extremely hard to predict. And I think that's part of what we're encountering right now.
Absolutely. It's the uncertainty in ice is the largest uncertainty. I was just saying that there are other things, as I say, the heat content of the ocean that
no, I don't disagree with you.
But the point you make, and again, it emphasizes the importance of the book. Our future, in many ways, is going to be determined by the regions of the world that we tend to not think about a lot, the polar regions, because ice is ultimately going to determine in so many ways the future of the world. And the point you just made about resilience, I think, is important because, I'm giving a short shrift because there's a fair amount of discussion in the book about it. But I think it's an important issue that we don't always know resilience. I mean, doom and gloom scenarios often overestimate, and polar bears are an example. You point out, I mean, everyone's seen the pictures, the poor polar bear floating on a little ice floe.
Starving, yeah, exactly.
But in fact, as you point out, genetic evidence suggests polar bears have survived in warm climates. So it's not clear that, that biology is resilient in many ways. And so one can make assumptions about extinction, but those assumptions are not always right. So
that's right. The polar bears, when it warmed in the past, the polar bears retreated to islands like Svalbard or other places further north. They interbreeded with brown bears. They gained new kinds of genes, and then their populations hit a bottleneck. But when it cooled off again, then they expanded their range. So, we really kind of don't know. It's hard to predict extinction risks for species that can migrate so much and interbreed so much with nearby neighbors.
Well, let's let the last thing I want to mention be, so the good news is that polar bears may not be gone. I've gone up and seen polar bears, and I'd hate to lose them. They're lovely to watch. But one thing that is a real concern, or at least it's worth understanding, and when we talk about the fact that our future will be determined by ice, there's a lot of ice under the ground, and that's the name of permafrost, and that it maybe is almost of more concern than glaciers in terms of affecting our future.
Absolutely.
And why don't you elaborate on it since?
Well, and we have, permafrost itself is an incredibly rich ecosystem. It contains, as we talked about before, an enormous amount of carbon because of microbial action over millennia. And it's a giant storehouse of carbon. So the first issue to really think about as we have a warming north is that we're setting off ever accelerating cycles. And this is where, when we say it's hard to predict, yeah, that's true. But it also, what we know suggests that we're going to enter feedback loops, which will only increase warming. And that is, as you have warming, you're melting the ice. When you melt the ice, the albedo effect changes in the sense that now we heat up faster. As we heat up faster, the permafrost melts. As the permafrost melts, you're introducing new carbon into the atmosphere. Enormous amounts of carbon. I mean, more carbon than's in the atmosphere now can enter the atmosphere, which will warm things up more. So basically, the more you know about permafrost, the more you know about the albedo effect, the more you realize that global warming sets up a series of positive feedback loops. That's why it's a concern that as you warm, you're setting up the propensity to warm even more through melting permafrost, which increases the carbon in the atmosphere, through changes in the albedo effect and so forth. But also more immediately, and this is just, really tragic, is whole towns in Alaska and Siberia are needing to move just because the permafrost is melting so fast. They have to move whole towns, whole cloth. Move them across, and
that's because
river
that's
bases.
Again simple physics. When the ice melts, water takes less volume, And so what was ice, when it becomes water, you get huge sinkholes and you get,
Oh yeah, and if you're by a river, that river will erode much faster,
yeah,
and so there are whole towns that are disappearing. I think the last calculation are 17 villages, towns in Alaska need to move. They've moved 2 of them already.
yeah,
When you work in Nunavut, you see whenever they have to build on permafrost, what has to happen in Nunavut territory. In Canada, if they're building on permafrost, because the melting permafrost changes what can happen to the structures on top. In Siberia, I mean, their whole cities are being affected by this, particularly cities that have refineries or plants that they're going to have to move them and restore them. No, it's changing. We're changing the geography of the Earth in timescales that we can observe and measure.
absolutely.
Not only is the ice melting, and that's the big piece.
Yeah, but everything else is there's all interconnected, and ice plays a key role. And I was thinking I should go back for people when we talk about albedo, maybe that's a technical term, but the bottom line is that ice is white, it reflects sunlight. Water isn't white, and it absorbs. So when ice turns to water, you tend to absorb more heat, and that's that feedback loop. But the key point you made is that things are changing, and our future is going to depend a lot on what's going on in the polar regions now. And I want to give you the last word by reading you from 2 other quotes from the epilogue. The epilogue starts with, "Moving ice has transformed our world. Homo sapiens arose during a rare moment in our planet's history, one with ice covering the polar region." So humans have arisen in a very rare moment in the history of the Earth. And we're just sort of insignificant in that sense. But the last paragraph I find is telling. "But rather than make us feel small and insignificant, polar regions can enlarge us. Scientific discovery at the poles reveals our deep connections to one another and to the planet. Here, life is only possible when humans look beyond themselves to survive, thrive, and adapt. Our existence on frozen tundra and ice is impossible if we do not learn from and collaborate with one another. And the more we look, the more we find that polar regions are themselves fragile places, ones that can change in a brief moment of geological time. It's profoundly humbling to find our own vulnerabilities, as well as our capacities for resilient growth and discovery in the most remote and delicate landscapes on our planet." And it has been fascinating to talk to you about that and everything else. As I say, I've always enjoyed our discussions, and I hope you've enjoyed it too. And we've done justice to what was a fascinating book and a fascinating discussion. It's been great to have you.
Thanks so much. That was a lot of fun.
It was a lot of fun for me too. Thank you. I'm glad you enjoyed it, and I know that people listening will have enjoyed it. Your enthusiasm and the fascinating stories are great. Thanks again.
Thank you.
Hi, it's Lawrence again. As the Origins podcast continues to reach millions of people around the world, I just wanted to say thank you. It's because of your support, whether you listen or watch, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you'd like to see any parts of the podcast improved. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at originsproject.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture. You can learn more about our events, our travel excursions, and ways to get involved at originsproject.org. Thank you.